Good morning, good afternoon, good evening, добрый день. My name is Vladimir Shiltsev. I'm a scientist at Fermilab National Laboratory near Chicago, Illinois. It's my pleasure and great honor to open today's event. Let me start my slides. So today we have physics, peace, human rights, Sakharov-100, celebrating Andrei Sakharov's contributions to science and humanity. The event is organized by American Physical Society, UNITS, Forum on the History of Physics, Forum on International Physics, Forum on Physics and Society, and Committee on the International Freedom of Scientists, and Russian-American Science Association. Both APS and RASA are non-for-profit organizations for disseminations of scientific knowledge. So we have an efficient organizing committee that consists of truly international and diverse. So Louisa Cifarelli, Christine Darf, Paul Halpern, Alan Hurd, Alexander Kabanov, Stuart Prager, Roald Tsagdeev, Cheryl Spencer, and myself. We've got tremendous help from APS. Without that help, this webinar wouldn't be possible. So particularly Alex Adams, Ebony Adams, Hunter Clemens, Amy Flatten, Michelle Irvin, and Sarah Monk provided a lot of support and help in organizing this event. So we would like to thank them very, very much. Let me outline very briefly Andrei Sakharov's key life moments. He was born on May 21st, 1921, exactly 100 years ago in Moscow. His mother, Ekaterina, was Orthodox and with a Greek descent. His father, Dmitry, was a famous physics teacher, and his problems in physics got published widely and disseminated widely in the Soviet Union over many, many years. So 16 editions were in print. So you can see on the right his book, very recent publication. So still very much used by students all over Russia. So Andrei Sakharov, Andrei Dmitrievich, it's a patronymic name because his father's name, Dmitry. Andrei Dmitrievich Sakharov graduated from Moscow State University in 1942. In 1947, he got PhD, candidate of sciences, so-called in Russia, from Physical Institute of Academy of Sciences, or also known as Lebedev Institute. In 1953, he got the second scientific degree, Doctor of Sciences, Doctor Nauk, habilitation. And same year, he became full member of the USSR Academy of Sciences. In 1948 till 1968, he worked on thermonuclear weapons. And around the same time, he got involved in the human rights and disarmament and these activities. So in 1975, he got Nobel Peace Prize for his struggle for human rights in the Soviet Union, for disarmament and cooperation between all nations. So these activities resulted in his exile in Gorky, which is now Nizhny Novgorod, from 1980 to 1986. In 1989, after all that ended, so he was elected in the USSR Parliament, Verkhovny Sovet, or Supreme Soviet, and Sakharov died December 14, 1989. His PhD dissertation of 1947 was Theory of Nuclear Transitions of the Type 0 to 0. His PhD thesis advisor and long-term collaborator was Igor Tam. Igor, together with Cherenkov and Frank, got Nobel Prize in Physics in 1958 for discovery and explanation of the Vavilov-Cherenkov radiation. Sakharov got numerous awards from USSR government. So here on top, for example, you can see 3 golden stars. These are golden stars given to heroes of socialist labor. So other awards are listed here. At the bottom, you see medals, which indicate that he was a recipient of the Stalin State Prize and Lenin State Prize. But in 1980, he was stripped of all the awards. This is the copy of the decree of the Presidium of the Supreme Soviet signed by Leonid Brezhnev. And citation is, because of the systematic actions of Sakharov Andrei Dmitrievich, denigrating him as a recipient of these state awards, and taking into account the numerous proposals of the Soviet public, he stripped off all the state awards of the USSR. So Sakharov was very well known in the West. For example, in 1974, an influential American weekly magazine, Saturday Review, in its 50th anniversary issue, published a collection of articles of the leading intellectuals from all over the world, including Sakharov, Werner von Braun, Kurt Waldheim, Isaac Asimov, Neil Armstrong, and Jacques Cousteau, and many others. So I have this copy of this magazine. So Sakharov's essay was extremely interesting. So he predicted at that time in 1974, when these people were asked to look 50 years ahead in 2024 AD, he predicted appearance of internet, which he called universal information system, not only with its pluses, but also with its minuses. So he also was talking about human habitat in the future to be separated in the working and living zones, predicted the flourishing of fusion energy, high temperature superconductivity, artificial diamonds, walking electron cars, which wouldn't require any roads, beginning of moon exploration, and of course his favorite political idea was convergence of the socialist and capitalist systems. In 1982, Marcel Decker, publisher, New York, published collected scientific works of Andrei Sakharov. So this is a very nice book, which contains all Sakharov's works translated and edited by a very efficient team by Terhar and brothers Chudnovsky. And it has 4 parts, plasma physics, cosmology, field theory, and elementary particles, and divertissements. So that's the book. Shortly after Andrei's death in '89, so a year later, Physics Today, our leading physics journal, published a very nice article on Andrei by famous scientists Sidney Drell and from USA and Lev Okun from Russia. So today we have an impressive list of outstanding invited speakers. Equally outstanding are our session chairs. The first session, Capturing the Sun, Sakharov's Contributions to Fusion and Energy, will be chaired by Roald Sagdeev. Roald got elected full member of the Soviet Union Academy of Sciences in 1968. He was Mikhail Gorbachev's advisor from '85 to '91, and since 1989, he is professor of University of Maryland. The second session, Understanding the Universe, Sakharov's Contributions to Astrophysics, will be chaired by Luisa Cifarelli. She's professor, University of Bologna in Italy. She was president of Italian Physical Society from 2008 to 2019 and president of European Physical Society in 2011-2012. She was chair of APS Forum of International Physics in 2020. So Kathy Campbell will chair session number 3, Peace on Earth, Sakharov's Contributions to Nuclear Arms Control. Kathy was CRDF Global President and CEO in 2006-2016. CRDF stands for Civilian Research and Development Foundation. Before that, she worked for the US State Department and was a leading expert on USSR-Russia scientific and technology connections from 1989 to 1984. And the fourth session, Roundtable Reflecting on Sakharov's World, will be chaired by Cheryl Spencer. Cheryl is a recipient of the National Scientific Board Public Service Award in 2010. She's retired from SLAC National Accelerator Lab, and she was chair of the APS Forum of International Physics in 2017. So all participants would have opportunity to ask questions. So at the bottom of your screens, you should see Q&A button. So you can type your questions there. These questions will appear and will be read to the session chairs and session participants. So with that, I turn the microphone to session 1 chair, Roald Sagdeev. Roald, please go ahead. Please unmute yourself.
Okay. I'm so proud to chair this session on the topic which is so close to my heart. Also because my perception of Sakharov phenomenon is very personal. I joined the University of Moscow as a freshman in 1950. And my first day in dormitory, in student dormitory, I met rather mysterious freshman who also joined. He came from the army. He was a few years older. And later on, I have discovered what was a mystery. The man was later became famous as Oleg Lavrentiev, who actually served as a kind of intellectual trigger to Sakharov's and Tom's idea of magnetic confinement and magnetic torus. And we will hear more details about it from our first speaker in this session, Dmitry Ruth. And so series of faithful event in my life was associated with Andrei Sakharov and his name. I learned about Sakharov more when I met him as a student sent to work on my diploma at Sarov. So for a few months, I had a chance to interact from time to time with Sakharov and a few other outstanding physicists. And I happily left with a university diploma, planning to become grad student of Lev Landau. But to no avail, Soviet government wanted to send all of my class from University of Moscow, the physicists, to Ural, to now is known as a Snezhinsk secret nuclear weapons lab. So Landau tried very hard to change this destination, and he succeeded to find a compromise with Kurchatov. I was left to work at Kurchatov, and the very first day when I visited the newly created fresh department inside Kurchatov's empire, it was a small lab formed to work on Sakharov and Tom's idea. And this paper, famous now, was completely classified. We were unable to use word plasma. Instead, we were using a word of high altitude, which means high temperature syrup. So no words about neutrons, only neutral points, and so on. And Sakharov's paper, as in classified form, was a Bible in my work in life during that few years of my life. Then jumping ahead, I had a chance to meet Sakharov from time to time at academies of meetings when I was introduced there in mid-60s. And I was witnessing transformation of Sakharov in what he became, human rights advocate, global thinker about convergence of the systems, and more and more. And 1975, I had a direct encounter with that particular issue and this career change of Sakharov. You may remember he was awarded Nobel Peace Prize in the fall of 1975. And it happened so that about the same time as working in a different area in space, I was responsible for launching and landing on surface of Venus, first Soviet lander, Venera 9 and Venera 10, a few days later. And while there was a celebration of that important success in space exploration, I was called to come to Academy of Science, and there was a very big day when government tried to coerce members of Academy to signed a letter condemning Sakharov. And it was a difficult moment for me. And I can tell you that I was so happy that I was out of this. I managed to say no, and I happily accepted punishment, stripping me from the list of nominees for Lenin Prize for landing on the surface of Venus. So finally, in a few years later, I got the Lenin Prize in a very good company of Boris Kadamtsev, Vitaly Shafranov, and Oleg Galeev for introduction of neoclassical diffusion, which was in a kind of extension of what Sakharov and Tam were thinking about plasma behavior in the torus, later called tokamak. So that's, I would not continue with, until the last moment, which ended when we were sitting close to each other on the same row in the Congress of People's Deputies. And I will treasure for the rest of my life official document signed to me that I was a confidant of Sakharov during election process of election to Congress of People's Deputies. Thank you. Let me introduce the first speaker of this session, Dmitry Ruth, my very old colleague and friend. He graduated from Moscow Physico-Technical Institute, but his research work from student years was associated with the Kurchatov Institute, with the same group working on controlled fusion. And he there made several very important contributions in theory of nonlinear plasma behavior, processes associated with heating of plasma by high energy electron beam particles and so on. Then we were together for a few years in Novosibirsk, published several joint papers. And Dmitry, before he finished his tenure in Soviet science in Novosibirsk, came up with extremely important invention, which is called gas dynamic trap, which is actually a different form of magnetic trap for high energy ions than Sakharov and Tam's suggestion, but is also alive and in good hands now, not only in Novosibirsk, but in University of Wisconsin. So I think it's going to be very prominent in future. And Dmitry is still very active. Thank you. Dmitry, your words now.
Thank you for this.
Dmitry, you're muted. Please unmute yourself.
Thank you for this very kind introduction. And then I go to the screen sharing. Do you see my screen?
Not yet.
Oh, very strange.
I pressed the share screen. What's that?
Maybe I should do that. It's I am sharing here. Don't know what. Oh yeah. Page one. Do you see the screen now?
Yeah, very nice. Thank you. Please go ahead.
And yes, I go to full screen. Oh, fine. So thank you very much. And thank you for really very kind and flattering introduction. So I will speak about first steps on the path to controlled fusion that were triggered by Andrei Sakharov's ideas. Before I proceed, I mentioned the sources that I have been using, although I followed this story quite closely when I was a young student and then a young associate at Kurchatov Institute in the early 1960s. I still refreshed my memory by reading these things. The most notable is Andrei Sakharov's memoirs. It's a wonderful book. I just wanted to refresh my memory of several points. When I would open the corresponding page, start reading, then I couldn't stop and would read the whole book. So it's really nice reading. Yes. As Roald Sagdiyev has mentioned, a trigger for Sakharov's interest to controlled fusion was a proposal by Oleg Lavrentiev. Roald has already mentioned the background of this interesting person who wrote a proposal of of electrostatic plasma confinement without having even graduated from high school. He, because of the war, he finished only 7 or 8 years of schooling. Still, he read a lot when he served on Sakhalin Island on the far east of the Soviet Union, and came up with this proposal. The proposal was sent to Sakharov because it mentioned fission reactions, and so it was thought by the higher-ups that it might be interesting for Sakharov, and it was interesting for Sakharov, who took time to review this proposal. At that time, everything there in this area was top secret. So you can see here in the upper right corner on the first page that it is strict secret, separate or special folder, etc. And of course, it's cancelled by declassification many years after that. And this is Sakharov's handwriting, his review. What is somewhat interesting here is that the date is here in the lower right corner, August 18, 1950. And it sets, so to say, t equal to 0 for the further events. So Lavrentiev suggested to confine hot deuterium gas by electrostatic field created by a set of concentric spherical grids biased to high voltages. Sakharov gave high marks to Lavrentiev ingenuity, and so he indeed was sent to the university, and where Roland has met him. But Sakharov expressed concerns in the practicability of this approach. But he writes in his memoirs, "My first vague thoughts of magnetic confinement rather than electrostatic confinement occurred to me as I read Lavrentiev's letter and wrote my reply. And an idea of magnetic confinement in toroidal, in toroidal systems emerged. In Sakharov's own words, the appearance of closed magnetic field lines is particularly evident when the interior of a toroid, when the current passes through the toroidal winding situated on its surface. And here is a sketch of the system that with the particle, it's now confined by to the gyro orbits moving along the toroidal field. The further work continued in a close collaboration with Sakharov's mentor, ADs, we call sometimes Sakharov by his initials, a mentor and colleague, Professor Igor Tam, as mentioned, Nobel Prize winner. In their collaboration, Sakharov focused on equilibria and overall design, whereas Tam worked on development of transport equations. The work occurred at a very high pace. It was extremely intense work. Just in 2.5 months, they came up with general reactor concept. First, they realized that the purely toroidal field doesn't work because of the particle drifts in the toroidal magnetic field, and they understood that they necessarily have to drive a current around this torus, this inner conductor shows the current that creates the flux surfaces and eliminates these pesky drift effects. Classical transport equations have been outlined. There is everything there in in 3 publications that appeared eventually in the open literature in 1958 on the occasion of the Second Geneva Conference on peaceful uses of atomic energy. The pace of their work was indeed staggering. Already in October, Sakharov and Tam sent their proposal of starting a large-scale work in this direction to Igor Kurchatov, the scientific head of the Soviet atomic project. Sakharov authority was very high among the leaders of the Soviet atomic project, and by May 1951, the project was approved by the Soviet government. To me, this episode characterizes Sakharov's personality. He was a man who was not afraid to make bold decisions and then follow through with all his passion and energy, all risks notwithstanding. All this showed up again in the 1970s and 1980s when he began his crusade for peace and human rights. Now a few words of Sakharov's and Tam fusion reactor of 1950-1951. Its features were the use of deuterium as a fuel, no tritium and no tritium breeding then, water-cooled windings, toroidal current in a levitating coil, conductor, not shown in this figure. It was supposed to be situated somewhere near the axis. The major radius was 12 meter, minor radius of plasma 2 meters, thickness of the magnetic windings 2 meters, and toroidal magnetic field 5 Tesla. Some of these parameters are somewhat higher, the others are a bit lower, but in general they are not far from those that have been chosen for ITER. Other parameters of the reactor included the following. Central temperature was 100 keV by a factor of 5 higher than in ITER. It's because it was deuterium. Plasma density about factor of 3 higher than in ITER, and fusion power 0.9 gigawatt. Mass of the water copper winding was 13,000 tons, and ohmic power dissipating in the coil was 0.4 gigawatt. So the net power would be about half gigawatt, also not far from what ITER would produce. Specifically mentioned was a possibility of breeding uranium-233, and they would produce 8 kilos of this substance in 24 hours of operation. They mentioned expressly that it would then be burned in fission reactors with very high energy yield that would significantly exceed the energy released by the plasma. But the question, the nagging question was, how can one create a toroidal car? As I have mentioned, Sakharov suggested a very bold solution: to insert a metal ring into the fusion plasma and drive a current in this ring. In the present day fusion terminology, such a device would be called a levitron, not a tokamak. But obviously, it brought with this idea brought with it significant engineering challenges. Driving a current by radio, and Sakharov suggested some solutions for these engineering problems. He suggested to drive a current by radio frequency field with rectifying elements inserted into the ring, so it would be driven in a contactless fashion. Suspend the ring by applying a horizontal component of the additional and the weak cusp magnetic field, 100 Gauss. So it will be resting on this magnetic field, levitating indeed. And some ideas of the cooling of the ring have been mentioned, but remained vague at this stage. Eventually, they came up with the idea of a tokamak proper, as we understand it today. They called it second method of anti-drift stabilization. The second method, as they wrote, was technically much more admissible, in which it is therefore necessary to examine carefully. Sorry, I'm close to the end. It is not clear if yes, the formation of the axial current directly in the plasma by the method of induction. It is not clear if in using this method, the high temperature plasma is not destroyed at the moment when the induction current vanishes. And indeed, of course, major disruption is one, a possibility, and a pretty catastrophic one. And this would already be what we call today tokamak. An acronym was invented a few years later by Igor Garwin. Unfortunately, the further pace gradually slowed down. The enormity of technical problems and the lack of funding have slowed the progress worldwide. The slowing down even gave rise to the following, I would say, very unpleasant to the fusion year saying. The fusion is always 50 years away. Hopefully, in the next 50 years, the first commercial fusion reactor will finally appear. Now I just mentioned another contribution, Sakharov's contribution to fusion. This is invention of the Magneto explosive generators and their use for fusion research. The idea was to implode a conducting cylinder where axial magnetic field would be created by high explosives situated outside that would compress this conducting cylinder and thereby increase the magnetic field inside. And indeed, in the very first experiments, the magnetic fields up to 2 megagauss have been achieved in substantial volumes, as tens of cubic centimeters, convenient for a variety of physics experiments. At present, it is used for one version of the pulsed fusion power. Now, my last slide, I finish with quotation for the memoirs. Sorry for a typo. I quote it from Russian version. Somehow I couldn't find it in the English translation. The translation is therefore mine and imperfect, but still I read it. It's quite possible that controlled fusion facilities will be a basis for the energy generation in the 21st century. That's when we live, that we live in. My participation at the early stages of the research is so important for the future of humankind, are a source of great satisfaction to me. Thank you.
Thank you, Dmitry. Now we are moving to second talk, And I would like to introduce Bruno Coppi, but he doesn't need introduction. Everyone knows him. He's since long time in this field of science and in adjacent areas of astrophysics and space physics. And I can tell you how much I enjoyed working together with him, starting with almost a year we spent together in Trieste in a company of Marshall Rosenbluth and few other good friends and colleagues. And Bruno was a driver of many interesting initiatives. One particular contribution we did together, a joint paper with him and Marshall at Trieste time, was considering what could be impact on future tokamaks of a threat which may arise from different type of micro instabilities, which was initially mentioned by another prominent world physicist dissident, David Bohm. So with the notion of so-called Bohm diffusion, which could be very detrimental for any controlled fusion idea. So we finished the article suggesting that likely it could be reduced by quite substantial factor. Instead of Bohm diffusion, it would be gyro Bohm diffusion. So Bruno, you can speak now.
Well, thank you, Rolf, for your introduction. You know, we have long-time friendship, and maybe all this subject would require a great deal of time. But let me say that I had been, besides working in fusion and other areas, being concerned about human rights issues. And I was, in fact, the chairman of the Human Rights Committee, or the Committee for the International Freedom of Scientists of the APS, and also a small committee that was concerned with Sakharov. Rolf may remember that when he came for the first time, him and Yevgeny Velikov came to Boston, and we had a dinner for that. But so my acquaintance with Sakharov, also through his family, was in the second part of his life. And so he's beginning to speak. I cannot avoid speaking about what is the situation of freedom in science today. And let me repeat quickly some opinions that were voiced at the American Academy of Arts and Science. That is, in science today, the diversity, ethnic and other one, is increased relative to old time. But the diversity of thinking, and Professor Spencer of Harvard was very strong on that, has diminished. Not only, but there has been an emergence of large administrative structures that have taken hold of research frequently. And in fact, in case of fusion research, it delayed even the possibility of proving the scientific feasibility of fusion by decades. And all of us underestimated that effect, let me say. Now, the techniques that have been used, they are very similar to those, even in the Western world, similar to those that are attributed to the Soviet Union. For example, one of them is the damnatio memoria. In the Roman time, they would cancel the memory of everything, that of people and families who had done something, destroy the statues and so on. This is being practiced, still being practiced. And for example, some of the most disastrous effect of this is that in the name of a world project that Rolf may remember started with the good intention to stop the Star Wars, that was ITER originally, and also the original idea to have a world project is also good, but then it took a direction that none of us advocated. Some of the consequences of this is that major experimental programs were destroyed because of that. In particular, at MIT. At MIT, we had developed the Alcatel program. The Alcatel program was a drastic change from the original tokamak device. That is, we introduced the so-called air core poloidal field system, which gives the possibility to create very different configuration and induce large currents, much, much larger than those predicted by Tam and Sakharov, in small dimension, and even with magnetic field, high magnetic fields. The reactivity in a fusion plasma goes like the fourth power of the confining magnetic field. So going up in the field by factor 2, 3, and 4, we made a major difference. Now this solution had been adopted. In fact, now what is called tokamak is a mixture between the original tokamak and the Alcator. The name was taken from the Latin high field torus, alto campo torus. But again, there is on that, if I may complain, there is a damnatio memoriae effect. The cancellation of the Alcatel program at MIT, and now that is going on of the Frascati torus program that had been active in Italy, and parallelly the results of MIT are two examples of the intolerance, that may exist in the so-called scientific community now. Even the theory program, my program was canceled, but I still wait to survive in spite of that. But that gives you an idea of why the prediction that Sakharov made that we would have fusion by 24 was not made. There were no real difficulties. We need to try to prove scientifically that it can be done. There are many, many problems, in particular the fact that thermonuclear plasmas are not thermal. They are dominated by collective modes. And in particular, there are versions of the so-called Landau damping that are very important. There are important contributions that Roll and this collaborator made, and so they have to be checked by the experiments, and they have to be exploited. So that was not done. And so the story that fusion is 50 years away and so on, because it's so difficult, is not true. Let me mention that Asimovich did used to say, we will have fusion when we will want it. Now, let me say something about the Alcatel program. Many years ago, after we were in Trieste, I went back to the faculty of Princeton. Then I was invited to go to the institute with Marcel Rosenbluth. And there, Johnny Wheeler, as soon as I arrived, jumped on me because he felt that I should get interested in what is called now black holes. And we both agreed that it doesn't make sense to study black holes without matter, without plasmas. And we predicted they would have been discovered, as they later were discovered, by the X-ray emission that plasma around them would do. Let me say that today, this is still a very unpopular idea. Now, general relativity, of course, is highly valued. It's very important, but black holes without plasmas around them, they don't make sense, basically. Recently, the discovery of gravitational wave emitter brought the interest to binaries. But the work on binaries of the plasma that can surround the binary, where the gravitational potential is not symmetric, is not steady state, there's very few of us interested in it. So I'm mentioning that because in addition to a lack of freedom for thinking, there's also been a segregation of discipline. We separate ourselves in disciplines and we don't communicate. This did not happen in during the lifetime and during the professional times of Sakharov. In fact, in astrophysics, correctly, people speak about multi-messenger approach, which is the correct approach, but we don't practice this, unfortunately. Now, coming back to fusion, I already explained to you that the Alcatel machine of MIT was a departure from the tokamak with this new invention of technological type. But since we wanted with that machine simulate the plasmas that were surrounding black holes, and in those days, at MIT in particular, black holes were not well accepted. But we got the goal, we put the goal to get densities of the order of 10 to the 15 particle per cubic centimeter. Now, it is well established that black holes, the galactic ones, the small ones, in fact, have densities of that order. Well, the Alcatel machine produced those densities. And by the time they produced, the astrophysicists turned away from plasmas. But it became important for fusion research. And the major contribution was made by Sergei Mirnov from the Kurchatov Institute. He discovered that these plasmas that we had made for black holes were very pure, besides being well confined. And this is what you need, plasma purity and good confinement. Now, at this time, the most promising approach to fusion, even officially in the US, is that of the compact fusion reactors that follow the line of Alcatel. So this is great satisfaction. But let me say the one idea that came up during Sakharov time and then again rephrased by our friend Yevgeny Velikov is that with the physics results obtained with the Alcatel, it makes very high density, and the reactivity goes like the square of the density. So the high-field machine, they're very good neutron producer. So Evgeny proposed that we begin to study hybrid reactors, which are based on this high-field experiment. They don't need to be steady state. They don't need to ignite. And they could be used, for example, for a hybrid thorium. And then another friend from Washington, Kurt Bolton, now at the DOE, proposed that we operate with deuterium, because with the high field approach, you can burn not only deuterium-tritium, which is the easiest thing to do, but also DD, deuterium, and D-helium-3, that will be a very clean reactor. So the future of fusion is certainly very good, but we need to break away from this limitation of thinking and being compelled to adopt only one single approach. Let me say one final word about plasmas in the universe. Now, we know that plasmas in the universe at low energy and high energy, they're more important than ever before. Let me give you an example. We used to speak about cluster of galaxies, but by now we know that the galaxy clusters are mostly made of plasmas with temperatures that go from, let's say, 5 keV, and I was told by Shunyaev, even up to 80 keV. They are thermal and not thermal, and so on. They are the biggest object in the universe. They're certainly of concern to cosmology. And the same, the primordial plasmas. But the communication between the various communities is poor. With that, I think I will stop.
Thank you, Bruno. As usual, very interesting. And we will. I guess we are going to have a very good question and answer part of our session. So I would like, I invite the attendees to think now about important questions to our distinguished speakers. So now I'm using my prerogative to chair the session, and my old prerogative to be Sakharov's confidant in the People's Congress. I would like to pass Sakharov's baton to make fusion to our speaker representing a younger generation of plasma and fusion physicists, namely to Dr. Crystal Crombie, who represents Plasma Physics Lab at Military Academy at Brussels and Ghent University, and who is a very important member of ITER plasma physicist group, especially with her expertise in ion cyclotron heating as a very important component of fusion program. So, Crystal, your word.
Thank you. I hope you can see the screen.
Yeah, everything's fine. Please go ahead.
Yeah, okay. So thank you for the introduction. And it is my great pleasure indeed today to be invited to this event and to talk about the ITER project, the largest fusion machine in the world, under construction at the moment in the south of France. And ITER is the Latin word for the way, and it is indeed the way to a new, clean, safe, and nearly unlimited energy source. And the project is progressing very well, as you can see on the photo. This is a very recent view of the building site in Cadarache in France. And I will start with the main mission, the main reason why ITER was built, and a short history of the project. Then comes the progress on the machine assembly and the surrounding infrastructures. The Russian contributions will be highlighted as well, followed by the steps remaining before first plasma. Now, before starting off, I would like to stress here also the genius of Sakharov, who published in 1951, that is 70 years ago, a paper in which he considers some questions concerning the theory of magnetic thermonuclear reactors. And these questions, as he calls them, have indeed kept us busy for many years. They have turned out to be the most important concerns for fusion machines. And many years of experiment and research were necessary to now finally come to the realization of this first thermonuclear reactor, which will be ITER, because the acronym ITER means International Thermonuclear Experimental Reactor. And questions and difficulties were also part of the life of Sakharov. I think we will hear more about this during the rest of the event. In 1980, he was sent in exile to Gorky, now Nizhny Novgorod. And on the door of his apartment there, very interesting, he wrote, per aspera ad astra. And this is a Latin phrase, and this means something like, you can only reach the stars, astra, per aspera, by going through difficulties and hardships and endurance. And indeed, in fact, this summarizes the fusion project, the ITER project, very well. So now back to ITER. So what is ITER? The main mission, indeed, is to demonstrate now the scientific and technological feasibility of fusion power for peaceful purposes. And the machine will be a tokamak, and it was already mentioned that tokamak was the invention of Sakharov and Tam. And the dimensions you can see there were more or less predicted by Sakharov already. And ITER will demonstrate now the conditions required to produce burning plasma. In more quantitative terms, this means ITER is designed to have a capital Q above 10. This means that the fusion output power will be 10 times higher than the input power. The total power is around half a gigawatt, 500 megawatt is the aim, the prediction, and for pulses of at least 400 seconds. In an alternative mode of operation, ITER will operate in steady state with longer pulses of minutes, hours, at a Q lower, Q equals 5. And it will combine in one project all technologies needed for a fusion power plant. This is a very unique project, and indeed it started very early on. In fact, already in the first talks about ITER have dated back from 1985 during a summit in Geneva where Reagan and Gorbachev launched this idea of an international collaboration on fusion for the benefit of all mankind. It's a very noble project. Was of course only the paper version of it, and it took many decades, many years of discussions, political agreements, and so on, to then finally come in 2007 to the construction in Cadarache. And this is the picture on the top right. You see the very early phases of the construction, the leveling of the terrain there. And it went on for several years, and then we are now in the picture on the bottom right. That is the picture of today that I show you also on my title page. And you see the many new buildings that have been erected. And the big building in the central is the tokamak hall, where the ITER tokamak is being assembled. It is a global project, a global challenge. It consists of 7 members: China, Europe, India, Japan, Korea, Russia, and US. And they represent together 50% of world's population and 85% of the global GDP. And the final agreement was then, after many years of discussion, signed in 2006 in France. And on the picture, you might recognize the French president of that time, Jacques Chirac, and all the great leaders of the different partners who were present. And then in 2007, finally, the construction started. So why do we need ITER? Well, it's crucial in the progress for fusion, because ITER will allow us for the first time to study the influence of a large population of fusion-born alpha particles. The alpha particles are created in the fusion process, and they are charged, so they will stay inside the magnetically confined plasma core and heat the plasma. So the alpha particles determine the fraction of self-heating of the plasma from the fusion power. And if now you want to have net energy output, you need a high Q, and a Q equal 10, the ITER design requires then a self-heating of this by these alpha particles of 66%. And at the moment, you can see on the graph, JET. JET is the largest operating tokamak in the world. It's in the UK, near Oxford. And it is designed for a capital Q around 1, and it has a self-heating by alpha particles of around 16%. So the step from JET to ITER is a factor of 10, realized because of the bigger volume and also all the progress in the meantime. But basically, the bigger volume is a key parameter here. So the step from JET to ITER is 10, and then for burning plasmas, real reactors in future, we would like to go to a capital Q of 30, so another factor of 3. But you see, ITER is an important step to make. Now, where are we? Last year, in full pandemic, the real assembly of the machine has commenced, and French President Emmanuel Macron held an official COVID-proof inauguration to mark this event with high-ranked representatives of the 7 ITER members. And here is just one example of the different components of the machine. It is the cryostat. So the magnetic coils will be superconducting to allow for long pulse operation. That also means that the whole machine needs to be inside a well-insulated container, and this is this cryostat. And it's the biggest part of the machine because the whole machine is inside. It consists of 4 different pieces, and 3 of them have been assembled already. The 4th one, the top lid, is under construction on the ITER side. And on the picture on the right, you can see how the base section of this container is put in place in the tokamak pit, and ITER machine will be on top of this base section. Just to give you an idea of the complexity of the machine, this cryostat is a heavy piece. It weighs 1,250 tons, and it is constructed to a precision of 1 millimeter. So that is micro and micro scale in one go. And this is only one component of the machine, but next to the machine, there are also different infrastructures. For example, the electricity supply, the buildings for the additional heating systems, the neutral beams, the electron cyclotron heating, and also the cryo plant. The cryo plant mainly for the superconducting coils and for the cryo pumps. And this cryo plant in itself is also special. So it's not only the machine that is unique, but also this cryo plant is unique in the world. It's the largest concentrated cryo plant that's ever been built. And it has an installed cooling power of 75 kilowatts at 4.5 Kelvin, realized with liquid helium. And on top of that, also 1300 kilowatt at 80 Kelvin, realized with nitrogen. And also for this infrastructure, so this cryo plant, the functional tests have recently begun, beginning of this year, and are progressing. Now, since today we are celebrating, in fact, Sakharov's birthday, I would like to highlight a little bit the Russian contributions as well. As you can see on the map, many different institutes, universities, research centers, and companies work together to deliver components for the ITER machine. Few examples are gyrotrons for the electron cyclotron heating system, parts of the superconducting components, port plugs, plasma diagnostics, and many more. And all is coordinated by Anatoly Krasilnikov, head of ITER Domestic Agency for Russia, a very nice person who is overseeing all the activities that Russia is contributing for ITER. During the official inauguration ceremony in July last year with Emmanuel Macron, we had Alexei Likachev, Director General of Rosatom, who took part and who represented during this event, Vladimir Putin. As you can understand, since ITER is an international organization, also the people working there are coming from many different backgrounds. There is a team of about 1,000 people working who are employed directly by ITER, that is the central team, and 58 of them, 6% more or less, are from Russian nationality. But in reality, there are many more people involved because there are contractors and there are scientists like myself working from home institutes and contributing to ITER. And also there, many Russians contribute to the project in that way. So now, what is left to do? At the moment, the research plan for ITER and all the supporting research and development are being consolidated. They are published in 2 publications from the International Atomic Energy Agency. They are available. They are and they serve as the baseline document for the way ahead for the research plan that is going to be executed. And also, if you look at the timing, the timetable, main message from these graphs is to say that both the assembly of the machine and also the infrastructures are progressing very well and according to the schedule of 2016 when the last revision was made. So despite the difficulties that everybody had in the last year, but also ITER in terms of people not being available on site, but also deliveries not coming. But despite all this, we are still following the schedule of 2016 and first plasma is foreseen for 2025. So it's coming there. Now, in conclusion, ITER construction, as you have seen, has made enormous progress. Despite the challenges of the pandemic, but also the fact that many of the components were first of a kind. They've never been built before, everything was new. And the first set of major tokamak components have been delivered to the ITER site. I have shown you only this cryostat, but in fact, many of the main components are already on site and are now being assembled. Also, the surrounding infrastructure is progressing in parallel to the machine assembly. And of course, challenges remain. We need to complete the assembly, do the commissioning, demonstrate first plasma, and execute the research plan So it's a very ambitious project, still many years to come, or we will be very busy for many years to come. I think we should remember the main mission, the main goal of ITER, that it will allow for the first time in history to have a reactor-grade plasma at 150 million degrees, which is an important step for the global challenge of this clean and limitless energy. I think it's essential for all of us, for our well-being and our future as humans. And I think it's a nice way to continue what Sakharov, in fact, has started 100 years ago. And thank you very much for your attention.
Thank you, Dr. Crombie. It was a nice overview, and it's bringing what started by Sakharov to today's situation in fusion and high temperature plasma physics. Thank you again. Now I would like to alert all of the three speakers, all of you, to questions and open the question and answer session. We have still a few more minutes, I understand, in the deadline. So now I would like to ask for Alan, who agreed to help us with running this part of session.
Yes, Raul. I recommend the question from Stuart Prager. Perhaps he could open his voice channel.
Okay.
Oh, okay, thank you. This may be a question for either Roald or others that have known Sakharov. Did he pay attention to and have opinions and notice the fusion progress that was rapid in the 1970s and 80s? And did he take note of the Reagan-Gorbachev commitment to fusion that led to ITER, or did he play a role in that? So what was his view and observations in his later years about fusion?
Okay, let me try to answer. I had quite a few meetings with Andrei Sakharov, especially after he came back from Gorky, covering almost every aspect, you know, human rights, because I was involved in some of the debates against bad draft laws in Soviet parliament to other issues. SDI, of course, he was a member of committee of Soviet scientists working with with a group from National Academy of Sciences, which Dick Garwin played a key role, who is now with us. But I have to confess, never any technical issues related to fusion plasma we discussed. But I had some kind of feeling that he was reading at least papers and he knew what was going on. One particular dramatic case was in fall of 1985, when Gorbachev in Geneva during first summit made a preliminary proposal for joint fusion project to President Reagan. I was present there, and I felt so much ashamed because Sakharov, the real inventor, originator, was still in exile at that moment. And obviously, he was not asked to contribute to development at that time. But Gorbachev, about a year and a few months later, in December of 1986, he finally made this important move. He brought Sakharov back to Moscow to active life.
Raul, can I make an addition to what you said? This is Bruno. You hear me? I would like to make an addition.
Okay, please.
On the American side, I was consulted during those times by the State Department. And both on your side and our side, we were very much against the Star Wars, SDI. So on that basis, I thought that we, from the American side, we should support this idea. And But then it continued, it began to, so I think the goal was achieved. The Star Wars were never. So this is a success of ITER. The other one, that it is a war machine, but what became very early, very evident, they will go astray because of the big bureaucracies. Something that came out due to review was a monster thing. And we analyzed it under the Clinton administration. And basically, we convinced Clinton to get out. Then what happened, we went back during the Bush administration before the Iraq war. This is how we, and I think Stuart Prager, he was a witness when we had to vote on ITER within the US Department of Energy. But we did not expect it would take this role of being the only experiment trying to go to fusion and the longest possible, because the lady, Professor Krombe, spoke, she did not speak about the difficulties, technical difficulties that ITER will have in order to achieve those goals, and the probability that those goals will be achieved. But what was the time scale? And we don't know when it will get meaningful experiment in deuterium, tritium plasma. But the other aspect we did not predict was the terrorism, that anybody would be thinking differently, would be basically wiped out from the program. I am exaggerating, but that is the case.
Thank you, Bruno. Now we have to look. Alan, do we have any more questions?
You do have some. I
Maybe
think
we have time for
you
one
may
more.
be out of time. One more? Okay, then I recommend Vladimir.
Okay.
My question is to those who understand the landscape of the fusion ideas nowadays. Are there alternatives to inertial confinement which look promising and interesting? So, and are they pursued? So, hopefully, you have some quick answer to that question.
I think my suggestion is to ask now Dmitry Ruth to answer this. Yeah.
Thank you, Raul. Yes, there are alternatives. They are pursued at a modest level. However, they are, and some of them are alive and well. For example, the mirror approach that now has revived after many years of negligence, with understanding that the mirrors can be made in axisymmetric way that makes them really very simple and attractive. As in many other approaches, there are difficulties, of course, but this approach is pursued at Novosibirsk and now at Madison, and new facilities are being built. The old one have shown that quite an impressive plasma parameters, the one at Novosibirsk. Then there are other versions. A good sign in general is that some startup companies, some of quite significant scale, got involved. And for example, this Tri-Alpha Incorporated, they have built a very impressive machine that combines the mirror confinement with field reverse configuration, and are working hard to move on that. Maybe I also add that Sakharov, Andrei Sakharov, he certainly was interested in fusion, and again, if you can read his memoirs where he speaks directly about that, but he was disappointed by the slow progress, and one can see such statements throughout his work, although of course he kept hope that eventually, as he mentions again directly, this will happen in the 21st century. So let's.
Dmitry, aren't you missing laser ignition?
Oh, no, but the question was, as posed verbally, say alternatives to ICF. So I mentioned only something in the magnetic fusion arena, but in ICF there is also a lot of life, both in Livermore and in Sandia and some French labs. But Sakharov was not particularly interested in that because it's would bring the whole way of thinking closer to the other behind the fence part of the world.
But there is a breakthrough, Dmitry, in inertial confinement that will become public in about 2 weeks.
Mm-hmm.
Oh, interesting.
Yes, yes.
So thank you very much to all of you, three of you speakers at this session, and to organizers, to audience. I think now we have to we can pass the baton to the next session. Thank you.
Hello. So we start now session number 2, which is devoted to the contribution of Andrei Sakharov in the understanding of the universe. I'm very pleased and honored to be part of this event. And before describing a little, introducing the session and in my eminent panelists, I would like to just give a small recollection about the visit of Andrei Sakharov and Elena Bonner in Italy in 1989. It was in February, and he has been triumphantly welcomed in Italy by the authorities, by the scientific community. He was received by President Pertini, by the Pope, John Paul II. It was really an incredible emotion and excitement throughout Italy. And before leaving, Sakharov went to Bologna, my university, where he was awarded the Laurea ad Honorem. And I really remember the pictures of the Aula Magna, so crowded, everybody was there. So this is a beautiful recollection, February 1989. And don't forget that the times were really special because in November that year, we witnessed the fall of the Berlin Wall. So it was really a particular moment of our, I would say, our history. So now let me come back to physics. In the mid-60s, Sakharov went back to fundamental science, studying cosmology, particle physics, and so let's say astrophysics at large. And he gave fundamental contributions to this sector of our science. We will listen right now about his contribution in understanding the baryon asymmetry of the universe, what is known as the matter-antimatter asymmetry, which is still an open question that neither the Standard Model nor general relativity have solved. He has given to us a strong and important legacy in this domain. And the other very interesting aspect we will discuss today is about the shape of the universe, the models that he brought, and also his view about gravity are extremely appealing. And to do so, to illustrate the contribution of Sakharov to understanding the universe, let me introduce the first panelist, the first speaker of this session, who is Professor Andrei Linde. Andrei Linde is one of the authors of the inflationary cosmology, which helps to solve many problems of the theory of the hot Big Bang. He's a professor of physics at Stanford University, but originally he worked in the Division of Theoretical Physics at Lebedev, at the Lebedev Physical Institute in Moscow. Professor Linde several times visited Sakharov during his exile in Gorky. And needless to say that Professor Linde has been awarded many prizes for his work. And let me just mention but a few: the Dirac Medal, the Fundamental Physics Prize, the Kavli Prize on Astrophysics, the Gamow Prize by Raza. And he's a member of the National Academy of Sciences of the United States and of the American Academy of Arts and Sciences. The title of his talk is Sakharov on Universe and Multiverse. So please, Professor.
Hi, I'm happy to be here. And it is my honor to speak at this conference. Well, let me immediately start with sharing the screen and then, oops, just a second, share, and then I'll continue. Okay, so this is about Sakharov, Sakharov's works after he started thinking about fundamental physics and left the study of weapons. His first works, actually, but before I'm going to talk about it, just two photos. This is Hawking and Sakharov, shortly after he returned to Moscow from the exile, and there was a conference on quantum gravity and cosmology, and they have met. And this is another conference showing, again, here is Sakharov to the left, here is Hawking to the right. And whoops, up near Hawking, that's me. I was much younger at that time. So I'm going to describe only three of papers of Sakharov which have written in this period. And that's because, in my point of view, they are most fundamental, maybe. And the second of these papers will be discussed in great detail by Rubakov in next lecture, next talk. I will concentrate on the first two and on the first and the third, and then a few comments on the second. So maybe some speculations on my side of what actually happens, how is that, what was Sakharov's approach to that, and why this strange choice of topics after he stopped, well, making explosions, theory, developing weapons, etc. And suddenly he turns into investigation for Big Bang, the Big Bang. That was his first paper. He himself considered it like a training board, jumping to theoretical physics from what he was doing before. And he started, maybe just for, again, my speculation about how all of this fits into his previous way of work. Well, he needed to invent a device which would just work. It may not be the most powerful, not be the most economical, but if you need to explode it, it just explodes. And then how to do it so that our absence of knowledge of the details will not, well, make it not working, because that was some of the crucial things at that time. So when he started studying cosmology, I think he inherited his previous attitude to that. Okay, we were able to make a very, very big bang, and now we're going to study the Big Bang, and let's try to think how I would do it, okay? How I would create, I don't think that he was speaking in these terms, but nevertheless, how I would do it in the way so that it works. And what we knew at that time, it was first paper 66, we need to explain where the galaxies came from. And the standard idea was galaxies came from, well, you had some inhomogeneities in the early universe. And then if you have a cloud of dust, then it compresses, etc., and then maybe start rotating, and then you get galaxy in the end. But where you got these first original perturbations, and well, maybe, well, they were just there, okay. So this made it kind of, well, you need to invent it. You need to explain where everything came from. And at that time, most of the people just trying to sort out what exactly were these perturbations from which galaxies were born, but how they originated, it was a second question. They were just there. You get one universe and it's given to you. Why do you think about it? Approach of Sakharov was different. He thought, well, if I started thinking about these perturbations, and they must be very, very special to produce galaxies, which we see right now, can we just avoid thinking about somebody cooking the universe, making these perturbations in a very peculiar way? What do we have without all of that? And without all of that, well, we have vacuum state. In a vacuum state, you always have perturbations. They're just, well, this is uncertainty principle. You cannot get rid of them. So is it possible at all to create galaxies from quantum fluctuations? Now, this idea is insane, okay? Quantum fluctuations are tiny, tiny. Galaxies are complete opposite to this tininess, to quantumness. It's the largest classical objects that we see in the universe, almost largest. So the way to think about it, it seemed crazy, but he thought, let me try to do it. And he had written a paper in '66 where he outlined possible approach to that. Well, the approach did not quite work because it was way too early. The necessary condition for this approach to work have been realized only with the invention of inflationary cosmology, and that's why I'm here. Okay, so in '81, Chibisov and Mukhanov invented a way how to do it. Inflationary cosmology tells you that the universe was tiny, tiny, and then it passes through the stage of exponentially fast expansion, and only after that it became hot as it was later. Okay, so Chibisov and Mukhanov studied consequences of one of the models of inflationary cosmology proposed by Starobinsky. And they said, okay, we know that galaxies could be formed by quantum fluctuations. I told them, are you insane? Quantum, it is a tiny, tiny, and you're talking about galaxies. And then I started learning about this, and I understood that this is actually a possibility. And they told me, and you know, by the way, that Sakharov was also studying this. Interesting. So nevertheless, this idea was so crazy, and not everybody took it well easily. But the basic idea is that quantum fluctuations exist everywhere. Then the universe, if it is at the stage of exponential expansion, then it stretches these fluctuations and they become large. And if the stretching is fast, then the amplitude of quantum fluctuations do not decrease during stretching. Then on the top of the previously frozen fluctuations, new ones appear and the new ones appear. The theory is complicated. I'm not going to explain you how exactly it works. It is really, really complicated. And as I said, my first reaction was that it's just crazy. Okay, but now in '92, Kobe satellite discovered perturbations produced apparently exactly this way. And then there were other investigations by other satellites and other experiments, and the best pictures are produced by Planck satellite. And these pictures show you the imprint of quantum fluctuations produced at the very beginning, well, of existence of the universe, approximately 10 to the minus 35 seconds after the origin of everything. And then they're stretched all over the space. And we are seeing right now, like using our universe as a photographic plate, the largest one possible photographic plate ever. And the people are getting Nobel Prizes for that. It took a lot of time to go from this pioneering idea of Sakharov to the works where the theory was really developed, and then to experiment for which people start getting Nobel Prizes. So that's one thing. Second work, as I said, it will be discussed by Rubakov. Standard approach for, well, matter, antimatter in the universe was that, well, we just have it, okay? You have a universe, you have matter, and we do not have antimatter, and that's just it. This is our universe given to us in one copy. Why are you asking so many questions? you can just assume that there were more baryons than anti-baryons in the universe. However, Sakharov tried to do different things. Suppose that there was no asymmetry. Suppose that everything was symmetric. Again, starting from something more natural, more general than inventing some numbers there from the very beginning. Okay, and then just try to obtain these baryons. And Rubakov will tell you the basic mechanism and how it will evolve later with Rubakov's contribution in particular. But as well, a person who studied inflation, I must say that without this mechanism, inflationary cosmology would be impossible, because inflation takes all previously existing baryons and dilute them exponentially. So if you later do not invent a way to produce them again, then nothing works. And then finally, it will be about, well, the vacuum energy in the universe. Vacuum energy is minuscule. It is in a natural, well, Planckian unit, so to say. It's 120 orders of magnitude smaller than what theoretical physics would expect naturally. Okay, and when I was visiting Sakharov and Gorky, one of the last visits, we discussed this problem and also the problem of inflationary multiverse, when the expansion of the universe may divide it into different exponential large parts with different laws of low energy physics in each of them. And he was, well, very happy to learn about this. And we also discussed recent ideas at that time of spontaneous compactification of multidimensional universe. And later, he issued a paper, how to solve the explain vacuum smallness of vacuum energy using tricks like that. And I simultaneously actually have written another paper with a different mechanism. So kind of we maybe will put each other into resonance. But his approach was easier, kind of more fundamental characteristic for his approach. And that is just some sentences from the paper, but basically it was like that. Suppose that our universe had originally huge dimensionality, many, many different dimensions. Then some of them squeeze it into some small something, and what remains is three space dimensions and one dimension of space. But these other dimensions, they could have many different ways of squeezing into something small. So if a universe has many combinatorical multitude, if there are many different possibilities to do that, then in different parts of the universe, you may have different energy of vacuum related to this multitude of different possibilities. So it was Sakharov 84. Nobody paid any attention, especially because it was based on anthropic principle, which at that time, well, not many people liked, and even now not many people like. But Sakharov, well, he has this attitude, humanistic, if you wish, anthropic was okay with that. So what happened later? Much, much later, it was 16 years later, there was some, necessity actually to solve this problem. And string theorists find out that in string theory, they start with 10 dimensions, and there are many dimensions squeezed into something small. And the combinatorical number of these dimensions is maybe 10 to the 500, or maybe even more. And in that case, you can realize the situation where the universe consists of many different parts. It could, there are maybe different branches of the wave function describing universe with different values of the cosmological constant. And when the cosmological constant vacuum energy is very, very large, then we cannot live there, because this rapid expansion of the universe at that time just tears the universe apart. And if vacuum energy is negative, and there are many such solutions also, then the universe just collapses almost instantly. And there is only one area, very, very tiny cosmological constant, exactly what we wanted to explain, where human life like ours is possible. So this is anthropic principle. This was 84. In 87, Steven Weinberg have issued a paper where he introduced this principle to those of us who would not read Russian literature at that time. And so it was 3 years later. Right now it's called Weinberg's solution with the cosmological constant problem. But that was 84, and it required so many years, almost 20 years, until string theorists recovered the possibility, the regime where this became possible. Then they became super enthusiastic about this. Then we do not know how exactly solve all problems of the string theory, which leads to this scenario. My main point is that several times in the history of physics, Sakharov said, well, introduced some ideas, which at that time could seem absolutely insane. And even right now, if you think about it, they, well, were really insane. And then they served as a basis for some major development in modern cosmology and particle physics. That's all. Thank you.
Thank you. Thank you very much, Professor Linde. And now let me introduce our next speaker. The questions will be at the end. Our next speaker is Professor Valerie Rubakov. Professor Rubakov is chief researcher at INR, the Institute for Nuclear Research of the Russian Academy of Sciences in Moscow, and he's a professor at the Lomonosov Moscow State University. Theoretical physicist, renowned of the world over. He made deep fundamental contributions to particle physics and cosmology. Just to name a few of his contributions: the Rubakov mechanism for proton decay, the mechanism for barogenesis in the early universe, the hypothesis of large extra dimensions. And he's the recipient of the Pomeranchuk Prize, the Pontecorvo Prize, the Julius Vess Award, the Hamburg Prize for Theoretical Physics, and many others. He's academician of the Russian Academy of Sciences, and he's also a member of the American Academy of Arts and Sciences. Please, Professor Rubakov, I understand that the title of your talk is Still Unsolved, Sakharov's Problem of the Cosmological Matter-Antimatter Asymmetry. Please.
Thank you, Lisa. I'm very glad and very honored to participate and give a talk at this meeting. Before I start, let me just, let me share the screen. Yeah. Before I start, let me mention that we in Russia also celebrate the Sakharov's birthday, and we had several meetings. We had today a meeting of the Russian Academy of Sciences together with Lebedev Institute. There is a monument which is inaugurated today at Sarov, where Sakharov worked on the nuclear weapon. There are several publications. One is very nice. If you have a chance, I strongly recommend. Very nice album with photos and many interesting recollections. And in Uspekhi, in Physics Uspekhi, the Russian review journal, which again, it was issued today, in today's issue of this month, we have a special part which is dedicated to Sakharov's birthday. So let me now come to my talk. The talk is indeed about the cosmological matter-antimatter symmetry. And actually, this is the problem which was
sorry, Valerie, sorry to interrupt you, but
yes?
we see a strange green square on top of your screen.
I don't know what's going on. I'm sorry.
Okay, I mean, we still see your slide.
I'm sorry,
it's all right.
I can't do anything about it.
Okay.
Anyhow, the problem that the composition of the universe is peculiar, that there is matter and no antimatter in the universe, was recognized by Andrei Sakharov back in 1966, actually, and the paper was out in 1967. And I should say that that was one of the first papers in the area of particle physics and cosmology together. I think this is probably the most important contribution of Andrei Sakharov into this area. The problem of the baryon symmetry or matter-antimatter symmetry actually stimulated a lot of research in theoretical physics, in particle physics experiments, and that's the topic of my talk. It is still unsolved, and that's a shame on us. We really do not understand how exactly the baryon symmetry was generated. So what's the problem? The problem is that we know what is the baryon to photon ratio of numbers, baryons and photons. It's about 10 to the minus 9. And there is no antimatter today, but if you go backwards in time to temperatures of about 100 MeV or higher, then there are lots of quark-antiquark pairs created so that the difference between the number of quarks and antiquarks in the current language, these are quarks. For Sakharov, these were baryons, protons, and neutrons. The difference between these numbers of quarks and antiquarks relative to the total number of quark-antiquark pairs was about 1 per billion. And that was unnatural to Andrei Sakharov. So he asked, how was this success generated in the course of the cosmological evolution? Very smart question. And indeed, as Andrei mentioned, today we have inflationary paradigm, which says, and any other, in fact, understanding of or model for very, very early universe tells you that initially the number of baryons and antibaryons, quarks and antiquarks should be exactly equal to each other. 0 in an inflationary scenario. Sakharov put this, his idea and the way he thought about it in a very short, concise way, which I just read. According to our hypothesis, he says, the occurrence of C asymmetry is equivalent of baryon symmetry. The occurrence of C asymmetry is the consequence of violation of CP invariance, important, in non-stationary expansion of the hot universe, again important, during the superdense stage, as manifest in the difference between the partial probabilities of the charge conjugate reactions. Very concise formulation. Today we are not as concise as Sakharov's time, and we say that there are 3 ingredients which are known as Sakharov conditions for generating this baryon asymmetry. These are baryon number violation. Obviously, if you start with baryon symmetric universe, you need baryon number violation to create asymmetric. C and CP violation to have different properties of particles versus antiparticles, and departure from thermal equilibrium, which means that you have to create something, not destroy the asymmetry. In thermal equilibrium, you tend to destroy everything. Okay, now let me go in historical way. There were early attempts, early suggestions, which were made actually quite substantially later than the Sakharov's paper. Until then, Sakharov's paper was not noticed very much. But then it became clear that that was an important thing to understand. And that was the time of ground unified theories, which unify all the existing forces except for gravity. And they have built-in mechanism of baryon number violation. The problem with them now is that the proton still doesn't decay, which means probably that we have to raise the scale, energy scale of ground unification even higher. And also, we need very high temperature, therefore, which is not very nice feature if you think of inflation. Now, the twist came later, and the beginning was the 12th understanding that baryon number is actually not conserved in the standard model, in the electroweak physics. This is a non-perturbative effect. It needs large field fluctuations, which are instantons if you think about 0 temperature, conventional particle physics, and these are enormously suppressed. This is the suppression factor, which is impossible to imagine, right? So, and that's why the proton is stable, right? because, you know, with this suppression factor, there is no baryon number violation whatsoever in the current universe. However, it was later on understood that large thermal fluctuations may be unsuppressed or very little suppressed, and they do lead to rapid baryon number non-conservation at high temperatures, which is just what is needed for in the early universe. The temperatures we are talking about are 100 GeV, relatively high, but not enormously high. Okay, so this opens up several possibilities. Let me mention a few of them. One is electroweak baryogenesis, meaning that the baryon symmetry can be generated by the very same baryon number violating processes that already exist in the electroweak physics, in the standard model. The problem with this is that the universe expands very slowly. We're talking about temperature of about 100 GeV, meaning that the expansion time at this epoch is about 10 to the minus 10 seconds, which is huge in particle physics standards. In particle physics, we deal with 10 to the minus 24 seconds, something like that. So we have 14 orders of magnitude to establish thermal equilibrium. And this is Sakharov's condition. You need to have deviations from thermal equilibrium. We have baryon number violation, but how about thermal inequilibrium? The only chance is that the universe underwent the first order phase transition, which is highly inequilibrium phase. We know from beginning of 70s, Kirchner, Linde, and many others have shown that at high temperatures, the electroweak symmetry is restored, the Higgs vacuum expectation value vanishes, and in principle, transition to asymmetric phase in the standard model with non-vanishing Higgs expectation value could be first order phase transition. And this is strongly in equilibrium process because it occurs via nucleation of small bubbles of microscopic radius, about 10 to the minus 16 centimeters, which grow almost at speed of light to huge sizes, millimeter or fraction of millimeter before the walls collide, and the phase transition ends up. So there is a possibility that the universe boils. It is strongly out of equilibrium process, and during this highly inequilibrium process, at the bubble walls, moving through the medium cosmic plasma, you may generate baryon symmetry in principle. Now, does this happen? Well, the answer is no, not in the standard model. In the standard model, we know today, it was not clear in the, say, end of 80s, but now it is clear that the standard model doesn't have the first order phase transition. With the Higgs mass of 125 GeV, the transition is actually smooth crossover. The second problem with electroweak baryogenesis is that in the standard model we have 2 weak CP violation. The CKM CP violation built in the standard model is too weak to create a sizable asymmetry. Is it the end of the story? Not quite, because the standard model may well be extended to something else, and this bigger theory may have extra ingredients which will save the day. What we need are extra bosons, which should relatively strongly interact with the Higgses, and also they should be present at the plasma at 100 GeV temperature, so the new degrees of freedom, new scalars, new bosons should not be much heavier than TeV. This is the energy scale probed by colliders. Now, we also need to have extra source of CP violation. Another Sakharov condition should be met. And this CP violation, it occurs, should exist in the scalar sector. So we should have several Higgs-like bosons and CP violation in this Higgs-like in this sector of Higgs boson. Even more generally, one may say that electroweak baryogenesis requires new dynamics in the electroweak symmetry breaking sector, and all this should happen at the energy scales of a few hundred GeV. So this is a question to colliders, whether there is such a dynamics which could allow for generation of baryon symmetry. Now, is this the only appealing scenario? No, of course, since Sakharov's paper, there were numbers and numbers of ideas and the scenarios, mechanisms proposed. And let me also now pause on leptogenesis. Leptogenesis is a very appealing scenario, which actually relates baryon symmetry and neutrino masses. We know that baryon number is violated in electroweak interactions, but there is a conservation law, which means in the standard model, B minus L, baryon number minus lepton numbers, is conserved. However, we know that lepton numbers, electron, muon, tau, are not conserved in nature. We know there are oscillations, transitions from one neutrino species to another in nature, and we know that neutrinos have masses. All this tells you that lepton number is violated in the standard model, in nature, not in the standard, in nature. And one way to generate neutrino masses, which we know, is what's called seesaw mechanism, which introduces a set of new heavy leptons, heavy neutral leptons, which are not charged against the standard model gauge theory, gauge interactions, and one introduces these neutral heavy leptons and mix them with conventional neutrinos, our neutrinos, and in this fashion one obtains masses of neutrinos which are naturally small. So leptogenesis is the idea that one can use the physics that's responsible for neutrino masses to generate lepton symmetry, which automatically is reprocessed into baryon symmetry by electroweak physics, electroweak mechanism. Now, the first attempt at this was actually successful, is to use the case of these heavy neutral leptons into conventional leptons, neutrinos, and Higgses. It is possible, once CP is violated in this neutrino sector, it is possible that the partial width, the probabilities of decay of the new heavy leptons into light leptons and Higgses is not the same as the decay into antileptons. And this naturally produces a symmetry between leptons and antileptons, and then baryon symmetry. What do you need for that? You need for that pretty heavy neutral leptons with masses on the order of 10 to the 9 at least GeV. And also, it happens that by looking at the mechanism, you need actually very light conventional neutrinos for this mechanism to work. And that's precisely what we have. So there is some hint that we are on the right track. It is a pessimistic scenario because we have to deal with very, very heavy new heavy leptons, new particles, which is impossible to produce at colliders or anywhere. Also, I should say that some people say that searching for CP violation in neutrino oscillations of our conventional neutrinos will give us hint or allow us to calculate the baryon symmetry. This is not quite true because CP violating parameters in our neutrino sector are not the parameters that are responsible for generation of baryon symmetry. We need CP violation of different sort to have the CP violation in heavy neutral lepton decay. However, there is a chance. The chance is that you can also generate lepton asymmetry and baryon asymmetry in the oscillations of these new heavy leptons. Let me not go into details, but what I should say that if you think of creation of these guys, of these heavy neutral leptons, at temperatures of around 100 GeV in the early universe, then this is an inequilibrium process. You create them, they oscillate, and if there is CP violation in the sector, then you can create lepton asymmetry in the end. This is the picture of what's called freeze out. And this picture works if initially it was thought that for that you need masses of these heavy leptons on the order of 1 GeV. And that's nice because this gives us chance to discover these feebly interacting particles at colliders or fixed target experiments. Now, today, we know that that's not the case. Actually, the whole range of masses of these new heavy leptons from about 100 MeV to huge 10 to the 12 GeV works. It gives, can give, for any of these masses, you can obtain the realistic value of the lepton and then baryon asymmetry. Here is a picture from a very recent paper where the horizontal line is the mass, the vertical line is the mixing parameter, and the allowed range is here. In this range, you can indeed obtain the required baryon asymmetry. So there is a huge mass range in which this is possible, but the range where you can search for these neutral heavy leptons is actually rather large. So it may be that indeed with the next generation of collider experiments in this relatively higher mass range or fixed target experiments ship at CERN, as an example, you may discover the heavy neutral leptons, lighter heavy neutral leptons of 100 MeV, GeV, several GeV mass. Okay, so let me come to my summary. To summarize, the baryon asymmetry of the universe is actually one of the few phenomena beyond the standard model of particle physics. We should understand that. That's not something that is possible to generate in the standard model. We know that the standard model should be extended, and the baryon asymmetry is the phenomenon that tells us that the standard model is not complete. The baryon asymmetry problem I consider as a strong motivation for theoretical and experimental studies in particle physics and cosmology. We need to develop theory of baryon and lepton number conservation in the standard model, and beyond the standard model, which is partially done, we need to develop a theory of inequilibrium process in ultra-relativistic cosmic plasma made of ultra-relativistic particles, in equilibrium, very high temperatures, very non-trivial theoretical development, which is again ongoing. We need experimental studies of CP violation and search for new feebly interacting particles at colliders and fixed target experiments. So let me conclude by saying that Sakharov, more than 50 years ago, posed the problem, which we still did not solve. Still, I think we can obtain a solution, find a solution in foreseeable future, but for that we need luck. So as with the controlled fusion, the ideas of Sakharov live very long and stay unsolved very long. So he was looking very far into future, and hopefully all these problems will be solved, and we'll understand in this case how the matter was produced in our universe. Thank you.
Thank you. Thank you very much for this view of the far-fetching ideas of of Sakharov. Now, time is our enemy, so let me introduce our next speaker, who is the director of the Joint Institute of Nuclear Research, JNR, in Dubna, Grigory Trubnikov, academician of the Russian Academy of Sciences. His interest is in high-energy particle accelerators, especially beam dynamics, and also ion beams, stochastic cooling, electron cooling. He has carried out experiments in the major laboratories in Europe and in the United States, and he's one of the leaders of the new heavy ion collider NICA, which is about to operate at JINR. So my pleasure to give the floor to Grigory Trubnikov, who will tell us about physics of dense baryonic matter. We heard about baryonic matter, search for phase transitions and critical endpoints, the NICA project, the NICA collider at Dubna. Please, Valerie.
Thank you. Thank you, Luisa. Yeah, thank you very much. I will try to. Do you see my screen? It's okay?
Perfect, yes.
Thank you very much. First of all, of course, it's a great honor for me to have a short talk today in such a ensemble of famous scientists, and thanks a lot to organizers of this event. As Valerie told, this event and this 100th anniversary of Andrei Dmitry Sakharov is a great society event in Russia. So my talk will be mainly about the project which we now develop in Dubna. You can see at this slide, Dubna is a very beautiful place to the north of Moscow on the Volga River banks, and in the right upper corner you can see the place of NICA collider location, which is now under construction in Dubna. So, well, of course, the heritage of Andrei Sakharov is a big bang for the science, and previous lecturers Valerie and Andrei told made the beautiful talks about the Baryonic symmetry and earlier universe. Well, my talk will be mainly about a bit later moments of our universe, which we plan to study at NICA collider, and is already, and the physics which is already studied in Brookhaven National Lab is first 10-20 microseconds after Big Bang, when the first elementary particles have been created, and quarks, gluons, and bosons and elementary particles started to formate the baryonic matter, the protons and neutrons, and this phase transition between quark, gluon matter and the baryonic matter is the point of interest for many ambitious projects in the world. They are RIC program at Brookhaven, the FAIR project in Germany, fixed target experiment at CERN, and the NICA collider, which we develop in Dubna. Well, our knowledge, the modern knowledge about nuclear or baryonic matter is given on this slide. So we know about quarks and gluons, C-quarks and antiquarks, the hadron structure, which we speak about, the quarks and antiquarks, which build baryons and mesons. Baryons are protons and neutrons. They consist of 3 quarks each, and 3 generations or 3 families of quarks on the right bottom slide, which are known at now. up and down, charm and strange, and top and bottom. Of course, well, there are a lot of questions why there are only 3 families, 3 generations of quarks, why their masses and energies are so different from generation to generation, and why they grouped by 3 to build protons and neutrons after several microseconds after the Big Bang. So there are a lot of fundamental questions, and as I told already, well, one of such fundamental questions is the phase transition between unconfined quarks and gluons to baryons, the protons and neutrons. And if you speak about, well, 3 broad scientific thrusts of nuclear science, quantum chromodynamics, nuclear and nuclear astrophysics, and fundamental symmetries, well, the quantum chromodynamics seeks to develop a complete understanding of how quarks and gluons assemble themselves into protons and neutrons, how nuclear forces arise, and what forms of bulk strongly interacting matter can exist in nature, such as, say, quark-gluon plasma. Nuclear and nuclear astrophysics seeks to understand how protons and neutrons combine to form atomic nuclei, including some now being observed for the first time, and how these nuclei have arisen after 14 billion years after the Big Bang. And why iron is stable, well, why the uranium is the last one, which is naturally exploited, and trans-uranium elements, which are artificially synthesized, what are the basic laws for the forming of atomic nuclei, and fundamental symmetries of neutrons and nucleus 6, what Valerie and Andrei told before, seeks to develop a better understanding of fundamental interactions by studying the properties of neutrons and targeted, well, single focus experiments, etc. So all we know about the strong interactions, QCD theory, well, the color confinement of quarks, neutral color for the baryons and color charges for quarks, and the asymptotic freedom when the forces becomes higher with the distance increasing between quarks. And well, the color confinement is about hot and dense QCD, where lattice calculations are used mainly. And if you speak about asymptotic freedom, this vacuum, so-called vacuum QCD, perturbative calculations, high energy domain. Well, on my understanding, the portal to the observable world is study of confined hadrons and ions, and which is used in experiment and applications. But the portal to the rest of particle physics is study of deconfined quarks and gluons used in Lagrangian, and the study of equation of state and parton distribution functions in this phase transition from confined hadrons and ions to deconfined, to quark-gluon plasma, quark-gluon matter. Sorry. Well, of course, we speak about the nuclear matter at extreme conditions. This phase transition we consider happened after about 10 microseconds after the Big Bang, and it was very hot and dense nuclear matter. Temperatures are much higher, much higher than, for example, solar surface. We speak about huge magnetic fields, and we consider that the nuclear matter is similar to perfect liquid of quarks and gluons with ultra low viscosity. And if you speak about the amplitude, about value of magnetic fields, you can see at this slide the well, strongest steady magnetic field achieved so far in lab is about 10 to 5 Gauss. The shortly achieved strongest main magnetic field 10 to 7 Gauss. The typical surface of field of radio pulsar 10 to 13, surface field of magnetars 10 to 15, and well, how can we reach those amplitudes or even speak about higher? The proposal is to have a ion-ion collision at collider experiments with about from several to 100 GeV per nucleon energy, and it is expected to achieve up to the 10 to 17 Gauss. So it's close to the densities which happened during this phase transition after the Big Bang. And one of expected examples, or say discussed examples of such an object in the universe, where we could find or notify such high temperatures and dense and ultra high densities, is a neutron stars. And well, by modern knowledge, the structure of this unique and exotic object in space, the neutron star is object of 20-30 kilometer size, with extremely high density in the core, is a billion of tons per per cubic centimeter, and various forms of nuclear matter build this object. You see at the surface is a nuclear pasta, nuclear with neutron matter. Then the next layer is neutron matter as a superfluid, and inside the core of this object is a so-called strange hadronic matter. It means the very dense nuclear matter with hyperons, strange quarks, and in the core the deconfined quarks, so-called quark matter. And also, well, one could discuss color superconductivity in such a phase. Well, the principal questions to the nuclear and hadron physics now, well, if you speak about nuclear interactions, what is the equation of state when matter and extreme pressure and temperature? Are our ideas about the Big Bang and its further evolution correct? Is the ideas about the phase transition between quark-gluon matter and nuclear matter correct? How after the Big Bang this quark-gluon matter with baryonic chemical potential 0 transformed into nuclear matter with chemical potential equal to unit? What is inside neutron stars, and do quark-gluon stars exist? And if we speak about quantum chromodynamics and hadron physics, of course, what I discussed already before, why do quarks never exist isolated? The problem, not problem, but the case of asymptotic freedom. What is the origin of quark back, or the quark confinement? Why are protons and neutrons heavier than their constituent partons? What gives the mass to hadron? And do nuclear forces affect the quark-gluon structure of nuclear and mesons? I spoke already that the relativistic heavy ion collision is one of considered and proposed experiments, and experimental data from relativistic heavy ion collider at Brookhaven gives us sureness, I would say, that we could discover the quark-gluon matter existence, which is impossible to see directly, but is possible, and the existence of such a matter possible only in comparison of theoretical predictions and observables. And signatures to quark gluon matter is observation of the viscosity disappearance. So strong interaction means low viscosity, and if we see the suppression of transverse momenta when particles from reaction decelerated by dense quark gluon matter, and if we see the strong elliptical flows which are in agreement to hydrodynamical laws, it could be signatures that quark gluon matter exist. And this slide in yellow rectangular, you can see the expected characteristics of the experiment. So it's very short time periods, several of 10 to minus 24 seconds, and number of quark, and the temperature of the system is 10 to 14 Kelvin, and the density of the system is 10 to 30 bars. And so it is expected to see the perfect liquid, which could be, as I would say, the time machine, because I mean, such an experiment could be, well, discussed as a time machine, because creating such densities and temperatures in the lab conditions, we could step to the we could model the conditions of the very early universe after several seconds of the Big Bang. So as it was mentioned already, we speak about the phase transitions and critical endpoints. All you know about phase diagram for water, 3 phase states, and phase transitions from ice to water to liquid, from liquid to gaseous, critical points where the matter could exist simultaneously in 2 or 3 phase states. And the same we use for quantum chromodynamics, similar phase diagram which indicates the various states of hadronic matter from ordinary nuclei to quark gluon matter. And such a phase diagram is effectively explored in heavy ion collision at very high energies, for example, Rickenbrook-Heaven and Large Hadron Collider at CERN. A phase transition occurs at a very low net baryonic density. It was indicated a crossover transition between quark gluon matter and hadronic gas in many high energy experiments. Lattice QCD rather well describes this region in phase diagram. I mean, this one. A first order transition is expected at the highest baryonic chemical potential or maximum baryonic density which exists in the core of neutron stars. Then there must be a critical endpoint here between the crossover and the first order phase transition. The area of this phase diagram is less studied experimentally and theoretically, and the project NICA, which I will briefly speak now about, is dedicated to exploring this region. So NICA is a collider experiment, but also have a fixed target experiment option, which already under operation for 2 years. We call it baryonic matter at nucleotron. It is 10 countries, 19 institutions, 250 participants, and the main detector, multi-purpose detector or mixed phase detector, is under construction now. You see many participants from all over the world. The size of this detector, multi-purpose detector, is comparable to the size of fuselage of Jumbo. It's about 7 meters in diameter and 12 meters in length. And the third option, so-called spin physics detector, also considered as a stage for after 2025. So this detector is now under assembly in Dubna. Detector will, the weight is about 1,300 tons. You can see the arrival of the magnet and cryostat for this detector here by water, by sea transport to Dubna, from Italy, from Genova to Dubna last autumn. And you can see we already in the stage of assembly of the detector. You can see the iron yoke.
Grigori, Excuse me, you have to conclude within 1 minute, please.
Yes, I need 2 minutes only, 1-2 minutes. Yes, thank you. So the cryostat, and you can see assembly, you can see the collider NICA architecture. So the 2 synchrotrons as boosters and the collider of 500 meters in circumference. You can see we started in 2017, 4 years ago, with a greenfield, and now it is already the construction is under completion. End of this year, we will complete the civil construction. You can see here examples of superconducting magnets, which are also produced and under the collider is under assembly now. You can see the tunnel for superconducting magnets at NICA, and this is a fresh actual bird view. Of course, our main goal is science, but also multiplying of international human intellectual capital. We live in the open world, and I would like to conclude my talk with 2 slides. One, I think, is very close to mentality of Andrei Sakharov. This is an example, well, of how the mega projects could unite the nations all over the world. When the value of new Fermilab's mega project was discussed at Congressional Joint Committee of Atomic Energy in 1969, Robert Wilson was asked whether there was anything connected in the hopes of this hugely costly project with the security of the country. And he responded, it only has to do with the respect with which we regard one another, the dignity of man, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in our country and are patriotic about. In this sense, this new knowledge has all to do with honor and country, but it has nothing to do directly with defending our country, except to help make it worth defending. And well, I would like to conclude my last slide with this beautiful monument to Sakharov and his wisdom about the development of science. I believe that humankind will find a wise solution to the complicated task of implementing grandiose, inevitable progress with the preservation of the human in being and the natural in nature. Thank you very much.
Thank you very much, Grigory. I'm sorry that time is very short. Therefore, we must conclude this session on the fundamental legacy of Andrei Sakharov concerning particle physics, cosmology, and astrophysics at large. I would like to thank all speakers. As far as the questions are concerned, there are some questions which were asked, and I will ask the speakers to answer them by writing their answer in the chat. Thank you very much. And now I will give the floor to Kathy Campbell. Thank you.
Okay, thank you very much. It's an honor to be here today and participate in the celebration of Andrei Sakharov's life and work. I never had the chance to meet him, but I certainly recall learning about him while I was working on the US-Soviet cooperative program in Magneto hydrodynamics in the 1970s, and then conducting research on the Soviet Academy of Sciences in the 1980s. As I recently reacquainted myself with Sakharov's work and writings, I was struck by his incredible faith in science and the ability of scientists collaborating domestically or internationally to solve pressing global problems. He believes that science and the scientific method should underpin all good policy decision-making. In fact, in his 1968 essay that was published in the New York Times, he wrote, quote, "International affairs must be completely permeated with scientific methodology and a democratic spirit, with a fearless weighing of all facts, views, and theories, with maximum publicity of ultimate and intermediate goals, and with a consistency of principles." He was, in a phrase that we use nowadays, a true science diplomat. But science diplomacy is not the subject of this panel. Our focus is an extremely important topic about which Sakharov cared deeply and on which he had a profound impact starting as early as the 1950s. And that topic is nuclear arms control. We have an incredibly impressive panel today that includes individuals who worked with Sakharov. I will briefly introduce each before they speak. I'm sure the presentations today will generate a lot of questions, and we invite you to post your questions in the Q&A box throughout the panel presentations. We've allocated a little over 10 minutes for Q's and A's at the end of our session, and we'll try to get it to as many of them as possible. Also, if attendees want to direct your question to a specific panelist, please indicate that in your question. And to our panelists, as a reminder, I will reappear on video at the 13-minute mark, and that is your signal that you have 2 minutes remaining in your presentation. Our first speaker is Richard Garwin, who is Fellow Emeritus at the IBM Watson Research Center. He is well known to everybody. He has had a long scientific career focused on research, invention, and advising policymakers and US presidents. He earned his PhD in 1949 from the University of Chicago, after which he taught at the university and worked as a consultant at Los Alamos. Garwin played a crucial role in the development of the first hydrogen bomb. He designed the device tested in the Ivy Mike shot in the Marshall Islands in November 1952. He worked at IBM's Watson Laboratory from 1952 to 1993, where he conducted research on a wide range of topics. His research laid the foundation for a great deal of modern technology, including GPS satellite navigation, color monitors, laser printers, and many other technologies. He also has been a strong advocate for arms control. He has testified before many congressional committees, advised US presidents, served on the US President's Science Advisory Committee, on the Defense Science Board, and JASON. From 1993 to August 2001, he chaired the Arms Control and Non-Proliferation Advisory Board at the Department of State. And he has been a longtime member of Pugwash and served on the Pugwash Council. Dr. Garwin received the Presidential Medal of Freedom from President Obama in 2016. With that, I will turn it over to you, Dick.
Thank you, Kathy. So you can see my slide?
Yes.
All right. I'm going to try to remain on time. I'm pleased to help celebrate Andrei Sakharov's contributions to science and humanity, and recognizing that without Sakharov, he wouldn't be here in order to help celebrate. Gosh. So sorry about that. Who knows what's happening? His contributions to fusion energy and to astrophysics have served as the foundation for the contributions by scientists the world over. His remarkable contributions to peace, as will be detailed by Frank von Hippel, are fragile and in peril, as is the existence of systems of government capable of managing the powerful tools for destruction that we have built, and that can be rebuilt, even if they are largely eliminated. So some background may help to indicate the scope of the problem and the uncertain path forward. My personal involvement with Sakharov was primarily in meetings of the United States National Academy of Sciences Committee on International Security and Arms Control, CSAC, but my friend and colleague Sid Drell was closer with him and helped disseminate some of his works. From Sakharov's 1968 book, Progress, Coexistence, and Intellectual Freedom, and some of his later writings, I see that he felt that even though peaceful coexistence was of critical importance, he believed also that it would not be achieved by a monopoly on nuclear weapons on the part of one power. And he played a major role in contributing to the Soviet Union's ability to burn thermonuclear fuel, deuterium, and powerful thermonuclear explosives, for which it could be cheaply and inexhaustibly produced. My own parallel involvement was initially purely technical. Appearing for my second summer as a consultant at Los Alamos in May 1951, I asked Edward Teller what was new. I heard from him the idea of radiation implosion that he and Stanislaw Ulam had published in a secret Los Alamos report on March 9, 1951. He asked me to devise an experiment that would persuade any skeptic that radiation implosion by an auxiliary fission explosive, a primary in current terms, could burn large amounts of thermonuclear fuel. On July 25th, I published a 4-page secret report with a large fold-out sketch of what would be tested as the Mike shot of the IV series on November 1, 1952, with a yield of 11 megatons, more than 500 times the explosive yield of the weapon used against Hiroshima or Nagasaki. The realization of the design and its test in 16 months was a spectacular success organized by Los Alamos director Norris Bradbury and largely assigned to Marshall Holloway to produce the 80-plus ton Mike design itself. The development of the US hydrogen bomb was motivated by the fear that the Soviet Union would accomplish that first. The IV Mike test ensured that our Soviet colleagues would test their own true solid fuel thermonuclear weapon in November 1955, the RDS-37 at 1.6 megaton yield. The US had demonstrated staged lithium deuteride fueled thermonuclear weapon in Castle Bravo, 15 megatons on March 1, 1954. In addition to a line of fission weapons that included the 100 megaton Tsar bomba tested on October 30th, 1961, with a lead fusion tamper at 50 megatons, Sakharov also proposed a powerful tsunami-inducing torpedo that has been revived in recent years by Russian leadership, on which I don't comment further. Immediately after the use of the 2 nuclear weapons against Hiroshima and Nagasaki in August 1945 and the conclusion to World War II, many scientists involved in the Manhattan Project turned their efforts to the control and limitation of nuclear weapons. Reinforced a decade later, July 9, 1955, by Bertrand Russell's issuing the Russell-Einstein Manifesto, warning of the consequences of nuclear war. The Pugwash Conferences on Science and World Affairs, from its first meeting in Pugwash, Nova Scotia, July 1957, created the opportunity for scientists of various states to present papers and to discuss what might be done to reduce the likelihood of nuclear war, among other existential concerns. Pugwash provided the opportunity for track 1.5 and track 2, that is totally non-official dialogues, extending far beyond the problem of thermonuclear war. We need to understand and work to counter the perils not only to governments and to populations, but also to civilization, by physical destruction, but also by pandemics, by the potential advent of a dark age, the rejection of fact and science. Long available to anyone in the world are reliable assessments of the effect of nuclear weapons, first published in 1950 by the US Atomic Energy Commission, with the most recent version a long time ago in 1977. Although the scientists involved in creating the first nuclear weapons and then the thermonuclear weapons of essentially unlimited yield could be heard in their views of the essentiality of control and limitation of weapons, and ultimately to the effect that a nuclear war cannot be won and must not be fought. That group has passed on, and other concerns and opportunities compete for public attention. The effect of a single nuclear weapon is not the whole story on a finite Earth. And the impact of multiple detonations and resultant fires can largely block sunlight, producing nuclear winter for months or years. In recent years, research has provided evidence that the detonation of even tens of Hiroshima-yield weapons in the tropics, for instance, in nuclear war between Pakistan and India, with strong insolation, sunlight, could loft fire-produced black carbon to the stratosphere, where it would persist for months while spreading through the northern hemisphere, a topic that has not received the attention it deserves by those with experimental and computing resources to investigate quantitatively the individual steps involved. If you click on the live links, you can see the actual paper I'm referring to. Sakharov himself discussed one of the global effects of nuclear weapons detonations, that of radioactive fallout, especially carbon-14, a 5,000 plus year half-life. Many people might contribute to the next steps to avoid nuclear war. These are difficult times in formal relations between the United States and Russia and between the United States and China. Nevertheless, individuals in each country continue to try to understand the hazards to the peoples of the world and how these might be abated by individual or joint efforts. In particular, I welcome China as a competitor in building semiconductors, in designing advanced automobiles, in space exploration, in countering global warming, and in work in medicine and public health. I think that the United States has lagged for the last 20 years or more in some of these fields. But I do not welcome the near automatic classification of China as enemy of the United States, rather than as a competitor. In sports, fair competition brings a gradual improvement of human performance. We should be doing the same in industrial and scientific competition. Free publication of results, resulting improvement need not be so gradual, as exemplified by the mRNA COVID-19 vaccines by Moderna and Pfizer-BioNTech, achieving initial mass vaccinations in December 2020. We have to survive the COVID-19 pandemic and future disease threats to humanity. An example, after initial months of confusion and secrecy, China has protected its people against the COVID-19 coronavirus pandemic, and the United States has already lost more than 500,000 people to the coronavirus, in part because of unwillingness to learn from China's experience. China's scientists published the full genome of the SARS-CoV-2 virus on January 11th, 2020, facilitating the production of vaccines all over the world. Both the determination of the viral genome and the creation of vaccines by those who had no samples of the virus itself were possible only because of the scientific progress over the past decades in many countries. Part of the problem in battling COVID-19 appears to be organizations that are unable to move rapidly in response to opportunities or threats, such as the US Centers for Disease Control and Prevention, CDC, and the World Health Organization, WHO. The problem is compounded by the ascendancy of fake news that drowns out analysis by recognized experts and innovators alike. This is novel over what we had in 1945 when people worked to abate problems of nuclear weapons. Another great physicist in January 1946 at a conference in Princeton commented to the question, Dr. Einstein, why is it that the mind of man has stretched so far as to discover the structure of the atom, we have been unable to devise the political means to keep the atom from destroying us? That's simple, my friend. It's because politics is more difficult than physics. Albert Einstein. Well, we would phrase the question differently, the mind of man and woman, and they contributed also to the atomic bomb and to the hydrogen bomb itself. But it's a deadly serious question with many aspects. Relatively few can contribute to the evolution of nuclear weapons or to the technical defenses against them. But scientists don't have a monopoly on potential solutions to the political realm. Especially in democratic societies, many people must share a viewpoint in order to make effective decisions. The doubling time of COVID-19 in the normal society of New York State in March 2020 was less than 3 days. Real-time control of such an epidemic, especially one for which there is no antiviral therapy, is possible only by following and modifying a predetermined plan, which we did not have. So who can contribute to the control of nuclear weapons and the prevention of nuclear war? The Pugwash conferences have contributed not only in their international nature, but especially in providing an umbrella that facilitated bilateral meetings between a small group of Soviet scientists initially and one of Americans, the latter led for many years by Paul Doty of Harvard. Some details of the Pugwash background to the 1972 Abm Treaty have been reported. Although I was not at the Pugwash conference in Udaipur, India, January 1962, where the Pugwash contribution to the Abm Treaty in 1972 got its start, I was well acquainted with the issues and the American participants. Persistence and mutual respect, honesty and effort were key to the advances in understanding the non-intuitive influence of imperfect missile defense on eroding deterrence. I've added this next paragraph. Key to such assessments are detailed analyses, such as that referred to by Sakharov in his 1968 Progress Coexistence work. Such technical publications are essential to the understanding of weapons and countermeasures and to defining agreements that might limit them. If attention is paid, they can also support a major tool of arms control, the defense planning and investment process in each country. A few centers in the United States, Germany, Sweden, China, and Russia, including the American Physical Society itself, have published technical studies that illuminate a field. This work should be valued and expanded. Our familiarity with Zoom and other remote conference systems, widespread access to the internet, and the experience of the past pandemic year that largely prevented physical meetings have provided new tools for proposing and considering new means of arms control. They need to be adopted by negotiators and decision makers themselves, with appropriate attention to information security, the necessary time scale, consistent with the urgency of the problem. Other aspects of political innovation seem unchanged. The necessity for significant group endorsement and discussion of specific approaches and the reporting of several such channels to governments. So I'm going to end there in order to save time for others. Thank you for listening.
Thank you, Dick. That was excellent and exactly on time. So thank you very much for that. And for linking the past with the present, which I think is good for the discussion period. So our next speaker is Frank von Hippel, who was Senior Research Physicist and Professor of Public and International Affairs Emeritus at Princeton University, where in 1975 he co-founded and co-chaired for 3 decades the Program on Science and Global Security. In 2006, he co-founded the International Panel on Fissile Materials and co-chaired it for the first 9 years. In the 1980s, he worked with Yevgeny Valeikov to develop a number of successful initiatives to end nuclear testing and the production of plutonium and highly enriched uranium for weapons and eliminate excess weapons material. He has advised US administrations and Congress on nuclear security issues since the Carter administration, During 1993 and 4, he served as Assistant Director for National Security in the White House Office of Science and Technology Policy and helped develop US-Russian cooperative initiatives on nuclear threat reduction. I joined OSTP just after Frank left, so I never had the opportunity to work with him, but certainly was delighted to build on all the work he had done. Dr. Van Hippel has met Sakharov. He first met him in February 1987, as I understand, and he served with him on the board of the Moscow-based International Foundation for the Survival and Development of Mankind. Frank, the floor is yours.
Thank you, Kathy. Let me just I actually first became aware of Andrei Sakharov, as many of us did, in 1968 when I read his book, Progress, Coexistence, and Intellectual Freedom in the New York Times. That such thinking could be coming out of the Soviet Union completely changed my image of the internal intellectual life in the Soviet Union. And I had the privilege of becoming acquainted with that later on. Let's see. So Sakharov, although he thought that it was necessary for the Soviet Union to have nuclear weapons to deter US nuclear threats, had no illusions about fighting or winning a nuclear war. And this is the picture that he painted of the consequences of nuclear war in 1968, after he emerged as a public figure after his life as a nuclear weapon designer with three awards of Hero of Socialist Labor. He said his image was a complete destruction of cities, industry, transport, and systems of education, poisoning of fields, water, and air by radioactivity, a physical destruction of the larger part of mankind, poverty, barbarism, a return to savagery, and a genetic degeneracy of the survivors under the impact of radiation, a destruction of the material and information basis of civilization. This is a measure of the peril that threatens the world as a result of the estrangement of the world's two superpowers. And now we have three. And this is unfortunately a situation that 50 years later is still with us. Now I'll describe briefly Sakharov's role in ending atmospheric nuclear testing, breaking the impasse between Gorbachev and Reagan over Star Wars, and what he had to say that relates to the current debate in the United States over the future of US shallow-based ICBMs. What was concerns about the genetic effects of atmospheric testing that first turned Sakharov into an activist. But initially, he was operating on the inside, promoting a debate over this inside the Soviet leadership. In the US, Linus Pauling went public with the same concerns and got thousands of scientists to sign a petition to put pressure on the US and the UK governments to agree to a ban on tests in the atmosphere. Sakharov says in his wonderful memoirs, in the years following the successful 1955 test of the third idea, that's which Dick Garwin already mentioned, the radiation implosion, I worried more and more about the biological effects of large nuclear tests. He estimated, and I've reviewed this estimate, and it stands up pretty well, that 10,000 human victims, that is, of genetic effects, cancers and other genetic effects, per megaton, of which he estimated 2/3 would be due to the carbon-14. we actually did test in the atmosphere collectively, the US and the Soviet Union, and to a smaller extent, other countries, 550 megatons of explosive power. So you can do the multiplication. But because of these concerns, Sakharov supported Khrushchev's 1958-61 test moratorium, where Khrushchev was trying to get an agreement on a comprehensive test ban going. And he urged a shift to what we now call and practice since since the 1990s in both in the major nuclear weapon states, science-based stockpile stewardship, which is basically laboratory experiments and computer modeling as an alternative to testing. Khrushchev rejected Sakharov's appeal not to resume testing in 1961. Sakharov remembered in his memoirs Khrushchev saying, "I'd be a jellyfish and not chairman of the Council of Ministers if I listened to people like Sakharov." But when negotiations on a comprehensive test ban treaty became stuck over the number of on-site inspections of suspect seismic events, the suspect that they were due to underground nuclear tests, Sakharov urged that the Soviet Union agree to a ban on tests everywhere except underground. And in the following year, sobered by the Cuban Missile Crisis, the Soviet Union, the United Kingdom, and the United States agreed to a limited test ban to which other countries eventually joined. With regard to ballistic missile defense, when a full suite of high-yield thermonuclear warheads had been developed, the attention of Sakharov and his colleagues during the period 1965-67 turned to other issues, including ballistic missile defense. And he says that they really achieved a consensus on two conclusions. One, first is that a way can always be found to neutralize an ABM system, an anti-ballistic missile defense system, at a considerably less expense than the cost of deploying it. And two, the deployment of an ABM system is dangerous since it can upset the strategic balance, by which he meant that it can advantage the side that strikes first. He says, in his memoirs, he says, these findings, which were apparently shared by American experts, probably helped pave the way for the 1972 treaty on the limitation of anti-ballistic missile systems. And in his 1968 book, he quoted an article by Dick Garwin and Hans Bethe in Scientific American of March 1968, which actually was the article which influenced me to get involved in arms control. The third contribution that Sakharov made was helping untie the package approach to nuclear reductions, what was called the package approach, which was linking deep cuts, which was of interest to both sides in the 1980s and later 1980s, and to ballistic missile defense, which President Reagan was enthusiastically boosting. At the first Gorbachev-Reagan summit in Geneva in 1985, Gorbachev made this linkage, and he said that he was very interested in offensive reductions, but there had to be limits on the U.S. Strategic Defense Initiative, the initiative where at that time was concept of space-based ballistic missile defense. Reagan refused. They met again in Reykjavik in 1986, and they agreed in principle on zero land-based intermediate range missiles, which became the 1987 INF Treaty, and to cut their strategic forces by 50%, which became the 1991 STAR Treaty. But again, they had the same impasse over ballistic missile defense. In December 1986, Sakharov returned from his 8-year exile in Gorky just in time to participate in the February 1987 International Scientists Forum for Nuclear Free World, which I helped Evgeny Velikov organize. There's Sakharov describes SDI as a Maginot Line in space, expensive and ineffective, and argued for abandoning, that Gorbachev should abandon the linkage, just let Star Wars collapse under its own weight. Garwin, Sagdiyev, Velikov, and others had been saying the same thing, but it may have taken Sakharov weighing in to give Gorbachev the final push. And he did drop the linkage, and we got those treaties. Now, looking into the future, today in the United States, I think we're committed to a process of modernizing all of our nuclear weapons and their delivery vehicles. But one leg of the so-called triad of intercontinental ballistic missiles, submarine launched ballistic missiles, and bombers is controversial. And I have some hope that maybe that won't be modernized, and maybe we'll be able to abandon it. And Sakharov explained in one of his speeches in that February 1987 forum, he said, a large part of the USSR's thermonuclear capability is in powerful silo-based missiles with multiple warheads. And I show what those multiple warheads look like on one US missile. Such missiles are vulnerable to preemptive strike by the modern highly accurate missiles of the potential enemy. A country relying mainly on silo-based weapons may be forced in a critical situation to launch a first strike. Today, silo-based ICBMs constitute the principal source of military strategic instability. Now, that was true then, and it's still true now. Today, US silo-based ICBMs have single warheads, but they are still on a hair trigger launch on warning posture, which gives the president less than 10 minutes to decide what to do if he's told that there's a warning of an incoming Russian or Chinese attack. Russia still has silo-based ICBMs with up to 10 warheads each. And it is believed that they too are on a launch on warning alert. So some of us, because we haven't been able to persuade our government to take our ICBMs off of launch on warning alert, some of us are urging that they be retired. So in summary, Sakharov contributed importantly as a talented weapons designer on the Soviet side of the development of the US-Soviet nuclear deterrence relationship in the 1950s and 1960s. But he was not at all comfortable with that relationship of mutually assured destruction. As an insider, he helped achieve the atmospheric test ban of 1963 and the Abm Treaty of 1972. As an outsider, he helped Gorbachev and Reagan achieve the INF and STAR treaties, the first treaties that actually reduced nuclear weapons. He did his weapons work as a brilliant cog in a huge bureaucratic machine. His arms control work he did as an autonomous human being. So thank you. Is anybody there?
Yeah.
Okay.
For some reason I can't pull this.
Okay.
Okay, here we go.
Yeah.
All right, so thank you very much, Frank. Our next speaker is Dr. Sig Hecker, who is an internationally recognized expert in plutonium science, global threat reduction, nuclear security. He is Professor Emeritus in the Department of Management, Science and Engineering at Stanford and a Senior Fellow Emeritus at the Freeman Spogli Institute for International Studies. From 86 until 1997, Sig served as the 5th director of Los Alamos. And he was very integrally involved in developing cooperation with the Russian nuclear laboratories to secure and safeguard the vast stockpiles of fissile material. So with that, I will turn it over to you, Sig.
Thank you very much, Kathy. Let me share my screen. And let's see if that works okay. Oops. Right. Okay, here we should go. So thank you. It's my great pleasure to be here to pay tribute to Andrei Sakharov. My association with Sakharov was never personal. I never met him personally. It was primarily through what he called the installation, and that is what we call the Russian Los Alamos, and that is in Sakharov, the Russian Federal Nuclear Center. I joined Los Alamos, I got to Los Alamos about 14 years or so after Dick Garwin did as a summer student. And I was at Los Alamos then for the most part, and saw the end of the Cold War. And the end of the Cold War, of course, dramatically changed our relationship with the Russians and with the Russian nuclear complex. I'll say more about that in a minute, but what it did was it brought me to Sakharov, the Russian Los Alamos, where I was invited almost exactly 20 years ago to help celebrate the 80th anniversary of Sakharov's birth. And I gave a presentation in Sakharov, and I'm going to choose a couple of the slides from that presentation as to how we pay tribute from the American side to Sakharov. And I talked about Sakharov the scientist, Sakharov the patriot, and Sakharov the humanist. Of course, today we've already heard much of Sakharov the scientist and his scientific contribution. We've also, of course, heard about Sakharov the patriot, and that is his contribution to the Soviet nuclear program, and particularly being known as the father of the Soviet hydrogen bomb. Oops. And I also presented this, sort of going back to 1968, to the treatise that's been mentioned quite a few times today already, and that is Progress, Coexistence, and Intellectual Freedom in 1968, where Sakharov really focused on the importance of the trinity of freedoms. That's also, of course, what got him out of Sakharov and out of the nuclear weapons program in 1968. But what Sakharov left, and then what I found when I got to Sakharov during my first visit, which was in 1992, just less than 2 months after the dissolution of the Soviet Union. And here we are on the upper left, where I am being greeted by Yuli Khariton, and he was the scientific leader of the Russian nuclear weapons program from the beginning. And I was there with colleagues from Lawrence Livermore Laboratory, John Knuckles and his colleagues, and Sakharov, of course, still stood very large in the history of Sarov. And on the right, here's the American team in front of Sakharov's cottage in the town of Sarov. And the reason that we were there was because the end of the Cold War, of course, changed the nuclear dangers enormously. The way that I like to put it is essentially changed the dangers from the hands, or at least from an American perspective, the hands of nuclear weapons in the hands of the Soviet government to now nuclear weapons and nuclear materials out of the hands of the Russian government. So the way the risks were viewed from the American side in 1992, sort of I put into the four loose nukes categories. And that is loose nukes, the weapons themselves, loose materials, loose people, loose nuclear exports. Those were the challenges at the time of the dissolution of the Soviet Union. And just to put some numbers on this, you can see that, of course, in loose nukes, we were talking about tens of thousands of nuclear weapons. In terms of fissile materials, it was this incredible amount of nearly 1.5 million kilograms of fissile materials, highly enriched uranium and plutonium. In terms of nuclear people, there were several 100,000 in the nuclear complex. And loose exports, of course, there was the concern of this huge complex with an economy in chaos at the time of dissolution of the Soviet Union. So we thought it had the making of a perfect nuclear storm. Of course, it was also the push for what we call the non-Lugar cooperative threat reduction program. But as you might imagine, for the two governments to touch on and work on these very sensitive issues, such as nuclear security, nuclear safety, the protection, controls, and accounting of nuclear materials, was exceedingly difficult for the governments to do with the lack of trust, after many decades of adversarial relationships. And that's essentially where the scientists stepped in to help in several of these critical areas. And that's where Sakharov's legacy came in. And that is that what we managed to do, and this particularly the three nuclear weapons laboratories on the American side, that is Los Alamos, Lawrence Livermore, and Sandia laboratories, worked with the equivalent laboratories on the Russian side. And the scientific area that we at Los Alamos were particularly interested, and the same for those in the Russian Federal Nuclear Center in Sarov, was this idea of Sakharov that's already been mentioned, and that is essentially flux compression of magnetic fields. And so we had Alexander Pavlovsky in Sarov, we had Max Fowler in Los Alamos, and our scientists then, when we first got together in 1992, began to work on collaboration in order to be able to further the scientific fields of the generation of large magnetic fields, as well as the study of materials under large magnetic fields. And so we actually did experiments, if you can believe that. Again, this was 1992, 93, 4 sort of time frame of where we were able to get our teams of scientists behind the fence in Sarov in Russia, and Russian scientists behind the fence that is in the classified areas of Los Alamos, of course, not viewing specific classified information, but getting within the compound of Los Alamos. And indeed, we did these experiments at Ancho Canyon in Los Alamos because in 1992 timeframe, 5 of these Magneto cumulative generators that were actually built in Sakharov were delivered to Los Alamos, and we did the tests with those in Ancho Canyon. And so, as we like to point out, the first Russian explosive device detonated on American soil was not delivered by an SS-18 missile, but rather by Federal Express, and this one in 1993. And in fact, here are a number of our scientists from Los Alamos, and as well as the Russian scientists working on one of these experiments in Sakharov in Russia. And indeed, these experiments led to enormous progress in the scientific field and what we like to call from megatons to megagauss. And indeed, at one point here, they generated the largest magnetic fields, generated by human beings. And this was in the area of about 15 megagauss. Eventually, this work led to a generation of about 28 megagauss. And the Los Alamos and the Russian scientists in this area managed over the period of about 15 or so years to publish 400 scientific papers together. It was that scientific collaboration that really then managed to build up the trust to allow us to tackle the really difficult issues of nuclear safety, nuclear security, materials protection control, and accounting that helped us to deal with the issue of the 4 loose nukes that I had mentioned. The other issue where Sakharov, of course, had a significant impact is in the area of nuclear testing. And Frank von Hippel has already mentioned Sakharov's contributions in this arena, where he was increasingly concerned about the harmful effects of radioactive fallout. That led then to the signing of the Limited Test Ban Treaty. And it also led, as Frank has pointed out, to the idea of doing things in other ways than just by nuclear testing. And this was Sakharov's proposal to Kurchatov back in 1958, where he actually said, look, we should redesign the nuclear devices so they can be deployed without testing, renounce the doctrine of needing tests, and then invest in computers, new calculating techniques in place of tests, and also to devise new experimental methods. And as Frank had pointed out, that in the end then was actually, this is what science-based stockpile stewardship was all about. But that wasn't until about 35 years later when Los Alamos, Livermore, and Sandia Laboratory worked together with the people at Department of Energy, particularly Victor Reese, Assistant Secretary at that time, to develop what we call science-based stockpile stewardship. So Sakharov had a significant impact on that from the Russian side, because they believed as much in the importance of science as we did in the United States. So then, just to try to get to the end, since I was giving this presentation in Sakharov itself, then I had learned over the years of the many, many visits that I've made to Russia, how important Russian history, art, and music are to the Russian people. And so I began to read much more. I began to go to the opera, of course, to the Bolshoi in Russia. And so I showed some of that in Russia. And here particularly is a quote from Anna Akhmatova, one of the great poets of the Russian times, where she said, when a man dies, his portraits change. And what I said in Sakharov was, well, that was not so for Andrei Sakharov, because his portraits were already indistinguishable from his legend during his own lifetime. And let me finish up with another great Russian poet, one who eventually was expelled and came to the United States and won the Nobel Prize in Literature where he said we'd light up the path that leads into death's realm, where never before until this point in time had any man managed to lighten a path. The old man's torch glows and the pathway widened. And that's exactly what happened with Sakharov. His torch glowed, the pathway widened for the rest of us. And what I said in 2001, which was just the beginning of sort of the change from the great period of the 1990s, where we worked together so closely, to all of a sudden seeing more and more restrictions again. And I said, you know, Russia's had this great abundance of poets and scientists. It needs them now to lighten up the path so that Sakharov's life was not lived in vain. I guess today I would say we need that just as much in the United States. And in fact, he needs his memories and our memories of him. We need to lighten up the path for the rest of mankind. Thank you for your attention.
Okay.
Yes, I'll stop sharing my screen.
Okay, and while you do that, I will start introducing our final speaker, who is Susan Eisenhower, the president of the Eisenhower Group Incorporated, which provides strategic counsel on political and business projects. She also was a founding director and the first president of the Eisenhower Institute. Ms. Eisenhower has served on many government task forces, including Department of Energy, where she served on the Baker-Cutler Commission on US-funded nuclear non-proliferation programs in Russia. She is an emeritus board member of the Nuclear Threat Initiative. Susan is well known for her work as a policy analyst, much of it focused on national security and related strategic issues. She has published extensively, and her most recent book is titled How Ike Led: The Principles Behind Eisenhower's Biggest Decisions, which was published in 2020. Susan, the floor is yours.
Thank you very much, Kathy, and thank you for that segue, because over the years I've become extremely interested in leadership, and especially strategic leadership. And I can say that enlightened leadership and the courage that drives it is in short supply today. That's why it's a really very big honor to join the commemoration of Andrei Sakharov's centennial. Andrei was outspoken, not just about human rights and political reform, but on the critical nature of arms control and stability. This integration of his interests with his own personality and the courage he demonstrated over many decades is an inspiration to us all, especially all the more remarkable given the times in which he lived and the repressive society in which he operated. Andrei's personal qualities continue to serve as an inspiration throughout the world, and in Russia, his voice is missed, but it's also missed in the United States, as Sig said, widening the path for so many who've come after. I wonder how he'd feel about the times we're living through today. Arms control seems to be all but forgotten, and certainly a lack of courage is evident everywhere. I like to think of Andrei's life lived out in chapters. First as a scientist, then as a human rights activist, and then as a champion of reform. I think Andrei learned over his life that dissent doesn't ultimately change the human condition, but that active work from within holds the promise. It's remarkable that after his 8 years in Gorky, he came back to Moscow and slowly, with the help of his colleagues, including Dr. Rold Sagdayev, managed to regain some of the important posts, such as that at the Academy of Sciences, to continue to press his views. I like to go back and look at people's origins to try and understand where these various qualities came together. And it's actually rather interesting. Andrei's grandfather, Ivan Sakharov, was deeply imbued with the social awareness and humanist principles. As a matter of fact, in 1905, his grandfather's book, I Cannot Keep Silent, regarding the evils of capital punishment, brought about a very big impact on Andrei. As a matter of fact, Andrei said, my grandfather's work on this book was an act of conscience and to an extent civic courage. Andrei wrote in his book Memoirs. His father, Dmitry, was a physics teacher who introduced Andrei to Igor Tamm, who won the Nobel the Nobel Prize in Physics in 1958. It was Igor Tamm who served as a mentor throughout his life. And his uncle Ivan was arrested several times in the 1930s. I'm sure that had a very deep impact on Andrei and his family. And then, of course, Elena Bonner, the activist and the light of his life. All of these influential figures brought about the man we were lucky to know. We have outlined in this session, particularly many of his arms control achievements. And I thank my colleagues, Dick and Frank and Sig for that. There are almost too many to count. But I'm intrigued by Andrei as a person, a human being. I first met Sakharov in 1987, the conference that Frank referenced on a nuclear-free world. And it was at that conference in Moscow that a sensation was created when Sakharov appeared again to express his opinions, just having come from not long from Gorky. Little could I imagine that I would get to know and indeed work beside Sakharov at the International Foundation for the Survival and Development of Humanity. At first, we thought our work was going to focus almost entirely around nuclear work. But as we found over time, Sakharov's outspoken opinions on so many levels and about so many subjects brought about a second informal mission to defend Sakharov and his views. It was actually unprecedented that Andrei, not long from exile, would be permitted to serve on a board in the USSR, the first Western-style foundation created in that country. And so I will recall the first meeting Andrei Sakharov had with Mikhail Gorbachev. All of the contradictions of a Soviet society emerging from the past was on full display for us. That meeting took place on January 15th, 1988. And at the Kremlin, each of us in Gorbachev's presence, actually requested by the president himself, was that each of us should make a few comments about the new foundation that had just been established. I'm afraid I didn't use my opportunity to any great moment, but when it came to Sakharov's turn, he produced a card with the names of 200 people, quote, prisoners of conscience still in Soviet prisons. Wow, I mean, this was amazing for the first meeting between Sakharov and Gorbachev. There was no wasting any time to get right to the point. Gorbachev had a ready temper, and you could just feel that it was beginning to flare. Gorbachev started rather hotly talking about the politics of realism, and that things had gone a bit far. And at the end, it was of this extraordinary meeting, I was privileged to hear Andrei Dmitryevich and Mikhail Sergeyevich have an exchange on the way out the door. Mikhail Sergeyevich, Andrei said, I have an idea about how to bury nuclear power plants underground safely. I would like to visit you on this. And Gorbachev, still shocked by what had happened at this meeting, said to him, why don't you do that, Andrei Dmitryevich? Come in and see me before you hold a press conference for the Western press, end quote. News reports of the meeting pictured Sakharov at a table, the table around which we all sat, but his face could not be seen. And in Sovietskaya Russia and Pravda, Sakharov's white hair was airbrushed black so that no one would recognize he had been at the table. Think of the extraordinary courage it took to continue his crusade, even after coming back from Gorky, in the face of what really felt to be a tightening situation. And then in November 1988, the situation was indeed hardening in the Soviet Union. Nevertheless, the work of the International Foundation was successful in bringing about Sakharov's first visit to the United States. As a matter of fact, we heard through the grapevine that the Politburo was so skeptical about Sakharov's trip to the West that they actually placed bets on whether or not Andrei would return. Of course, Andrei Sakharov returned. He had too much work to do, but the tightening indeed felt like an effort to roll back the excesses of perestroika, if not to silence the policy of glasnost altogether. Nevertheless, Sakharov continued his commitment to call out SDI, other arms control measures, and of course, his important work in human rights and in settling, especially the conflict in Nagorno-Karabakh. I had dinner at his home a number of times and had the opportunity to peer into the life of this historic giant. Nagorno-Karabakh was a very important issue for Elena Bonner, and in Sakharov's own way took up this fight right side by side with her. Concerns about the political economy and the environment in the country were always at the top of the dinner conversation. And I even had an opportunity once to ask him about what was the most important key development in the making of the the hydrogen bomb. He looked at me quizzically and said that it was possible. He was an enigmatic character, so often the case in the minds of a genius, but he was also the conscience of a nation. By virtue of his status as an icon, Sakharov was expected to be the man for all seasons, infinitely wise and all but infallible. But failing to see Sakharov as a human being was to rob him of one of his most deeply moving qualities. He had, perhaps in the course of his career, had some sympathy for Edward Teller, but stories will later go on to say how when they finally had an opportunity to meet, that it was an uncomfortable meeting, to say the least. Sakharov would not for a moment move off of his objection to the Strategic Defense Initiative, and Edward Teller, also a strong individual, stood his ground. I was also deeply moved because I think Americans have almost no capacity to understand the conditions in which these heroic scientists worked in the Soviet Union. Once I was taken to the Peter Kapitsa home to see the extraordinary living and working conditions of one of the Soviet Union's greatest scientists. And when I signed the guest book, I noticed that Andrei Sakharov had been there only days before to go through the archives. He was trying to piece together what had happened as he had been ousted from Moscow after his descent around the invasion or the imposition of forces in Afghanistan. And he was apparently looking through the archives to understand what Peter Kapitsa's position had been. How gratified he was to find out that Peter Kapitsa had defended Andrei Sakharov to the big bosses in the Politburo. An extraordinary indication of this kind of solidarity in those special circles in the scientific community. And finally, if I may end my remarks on a lighter note, I had an insight into his remarkable relationship with Elena Bonner. I will never forget, as long as I live, going to a nightclub with the Sakharovs on a trip to Leningrad during our International Foundation meetings. And one evening, we decided after a long dinner that we would go see the beginning of these new cooperative restaurants. And this particular one was a nightclub. It was called the Troika. It was a gaudy kind of place with flocked wallpaper. And there were many exotic dancers, including the French can displayed by some extraordinary looking women. And Elena Bonner leaned over and said, you know, Andrei's very upset that he's forgotten his long distance reading glasses. We didn't really quite know what to say, but Andrei kept complaining that he wanted to see the girls dance. He wanted to understand what this newfangled way was to spend an evening. So finally, Elena said, just go down to the front row. Just go, Andrei, go down to the front row, which he did. And as all of this unfolded, somebody, I thought rather cynically, yelled from another table. So is this the freedom you were fighting for? Well, of course, that wasn't what Andrei had in mind. He had bigger ideas in mind. He had the freedom that he gave up for some period of time, and the freedom he fought for all his life will be always remembered in those three extraordinary areas, in science, in arms control, and in human rights and political progress. Andrei will be remembered for his courage and his tenacity and his commitment to those integrated areas that were in his mind all part of the same way of looking at the world. He was a complex man, always thinking about the future with little regard or little desire to rewind the past. Ironically, however, his role as the savior of the nation and his development of the hydrogen bomb, the Soviet hydrogen bomb, gave him a measure of protection from the authorities. His other followers, Sergei Kovalyov and Yuri Orlov, spent time in prison. And yet Andrei Sakharov never stopped fighting for them and never stopped fighting for the political prisoners of conscience. Never let it be said that it is hard to imagine the world today without this historic trajectory of one man named Andrei Sakharov, this towering figure. So I'd like to end my comments by reflecting on Andrei Sakharov in his own words. In his memoir called Memoirs, he said, looking back on my life, I can see only actions which are a source of pride, but others which were false, cowardly, shameful, foolish, ill-advised, or inspired by some subconscious impulses better not to dwell on. While admitting all this in general terms, I don't want to linger on my failings, not out of concern for my reputation, but rather from a dislike of self-flagellation and public soul-searching. Moreover, I believe that no one can really learn from other people's mistakes. It's enough to learn from your own mistakes and to emulate the virtues of others. In conclusion, let me say that that courage and leadership that Andrei showed is indeed in short supply today. I wonder what Andrei would say about the failure of the international community to find strategic stability around cyber issues, and especially cyber issues in the context of our nuclear weapons establishment. We must redouble our efforts on arms control, the pursuit of peace, and the elevation of human rights to help make Andrei's contribution to the world a lasting legacy. Thank you very much.
Thank you, Susan. And thanks for sharing all those personal stories. I would have loved to have been a fly on the wall of that nightclub in Leningrad. All right, we do have a few questions and we have about 8 or 9 minutes, about 8 minutes. So let me pose them and I ask everyone to please be brief, no more than 2 minutes in your response. So the first one is from Bruno to Dick Garwin. There are signs of the beginning of a dark age as shown by the conduct of controlled fusion research. How should we react to this?
Oh, I think the dark age is much more problems of democracy and behavior in regard to global climate change and things like that. So fusion research has been underway for a long time. I would like to see more. I'd like to see more varied types, but we'll live one way or another. It could take a little longer.
Okay. The second question is directed to Sig. It's amazing that Sakharov convinced leadership to cut the yield of Tsar Bomba in half to 50 megatons. Is there a physical yield limit to the Bomba design?
So actually, Dick Garwin is the best one to answer that. But in the end, as Dick has often said, essentially there are no limits, to what you can do with a hydrogen bomb.
Yeah, in fact, the Russians have a linear growth. You don't have to make a bigger bomb. You could just add more components to it of the same kind. And it's not the most efficient way, but it works very well.
Okay, great. This question is for both Frank and Susan. Is there a source of optimism in these days of estrangement of now 3 superpowers?
Frank, why don't you go first?
Well, I think there's always hope, and I take my greatest hope from the conversations that we have among people in the 3 countries, and we're still there, still talking, and I actually have some hopes for the new administration, the new U.S. administration. Will be more constructive in this regard.
I would just first of all like to say yes. It's been such a pleasure to be here with 3 of my colleagues from that period after the collapse of the Soviet Union. I was lucky enough to go to Snezhinsk to do an evaluation for the Department of Energy on their work in securing nuclear materials and the rest of it. And I think it's up to all of us to remind the public of how much cooperation actually went on during that period of time. I was on a Zoom call last night in which Secretary Perry presented the recommendations in his book. I think they're outstanding. And I think we should use all of these opportunities to begin to make a case for nuclear cooperation, because I think there is a big drag in the system right now, and a lot of people need convincing that cooperation is actually one of the fundamental responsibilities of being a nuclear power.
Right. Okay, thanks. Let me take the chair's prerogative and ask a question following up on something that Sig said. You referenced the value of the trust that existed between the scientists when the laboratories started to work together in the 1990s. Do you think that that trust still exists between scientists in the US and Russia, or US and China? And if not, what can we do to rebuild it?
So the trust among the scientists still exists. However, because of the relationship at the top of our governments, we're no longer able to work together in the same way. And what it takes the trust, it takes the interest, and trust comes from respect. That's what I learned. When I first met them, I found out they're just like us, and their motivations were just like us. We respected their scientific capabilities. We were able to develop trust. So we had that, we developed it for all those years, but now we've not been able to work together essentially since about 2014. So because of the concern for that, what I've actually done is to sort of go down one level to the university levels. And I've created a program between Stanford and MEFI, the Russian Nuclear University, what I call Young Professional Nuclear Forums. And that is to bring the young folks together for them to build the interest, build the trust, build the respect. So if we can get the governments to sort of loosen the strings again, that we actually have the interest that's there.
Okay. Anybody else?
I just said, we're trying to do the same thing with Tsinghua in terms of having discussions of arms control possibilities.
Okay. So let me just finish with a question about the START agreement, which was renewed this past year. I guess I have 2 questions. First of all, as you know, the previous administration wanted to include China as part of the renewal. And I'm kind of interested in what your thoughts are on how Sakharov would have viewed that, and also what he would argue would be the most important priorities moving forward in this next 5-year period.
Shall I?
Yes, please.
I think ballistic missile defense is the biggest obstacle we have right now toward arms control agreements with both China and Russia, and it needs to be challenged in the U.S. In 2002, George Bush the younger took the U.S. out of that agreement with Russia. It was a terrible mistake. I mean, as Dick has explained to all of us. And Sakharov, I quoted Sakharov as saying that it's a waste of money, but what it does is it creates food for worst case analysts in China and Russia to say, well, we better build up just in case they can figure out how to make it work.
Right. Okay.
But only for worst case analysts, for people who build weapons and not only analyze, but respond.
Yeah.
Right.
Okay, well, we've reached the end of our allotted time, and I want to sincerely thank Susan, Dick, Frank, and Sig for participating today. And with that, I will turn it over to Cheryl for the next session. Thanks, all of you.
Thank you. Thank you.
Thank you.
Good morning, good afternoon, good evening. I'm Cheryl Spencer, the chair of the fourth and final session of our celebration of Andrei Sakharov's 100th birthday. This session is called Reflecting on Sakharov's World, and we will focus on his human rights activities and how, unfortunately, scientists and scholars are still being persecuted by governments in the West and the East, and what we can do to oppose violations of human rights and the suppression of academic freedom. We will hear from a physicist who worked with Sakharov to move the USSR towards constitutional democracy. We will hear from his granddaughter and stepdaughter, and from 3 scientists who are currently working to deter unjust attacks on scientists and to promote peace in the Middle East using science diplomacy. Sakharov's influence and contributions in a wide range of topics have been described in the previous 3 sessions, and his 100th birthday is being celebrated today in Moscow, in other Russian cities, in Lithuania, and in Boston, as well as here. And his granddaughter and stepdaughter are attending these other events. So we recorded a conversation with them earlier this month, and we will show that recording later in this session. But first, we will hear from Sakharov himself in a brief video recording made by a Soviet TV station in 1988, during which you will hear Sakharov describe his transition from being a hydrogen bomb designer to a political activist. You will see Elena Bonner, his second wife, in the video, and the English translation shows at the bottom of the screen. So please play the Sakharov video. Ebony, share your screen and show the 2-minute Sakharov. Thank you.
Я очень долгое время имел отношение к разработке термоядерного оружия. И я считал тогда, что это нужно для равновесия в мире. И продолжаю считать так и до сих пор. Но я одновременно понял весь ужас того, чем я занимаюсь, весь ужас того, что могла бы нести человечеству термоядерная война. Я начал также выступать против ядерных испытаний в атмосфере. В 1968 году я написал свое первое открытое общественное выступление, свою статью, которая получила большую известность. После этого сфера моей деятельности стала расширяться. Я еще стал много уделять внимание конкретным судьбам людей, конкретным людям. Так вот расширялось поле моей общественной деятельности, но определенный рубеж был, когда я был сослан в Горький. Вернувшись оттуда, я считал своим долгом в новых условиях продолжать делать то, что я считаю общественно важным.
Thank you, Ellen. Ebony, now I'm going to find my other speakers. So I'm going to bring up Boris Altshuler. And just a minute, I'm going to interview him, but first I'm going to spotlight him. Here we go. And I'm hoping everybody else will turn off their videos. Okay, so I'm very pleased to invite Boris Altshuler to greet us from the Lebedev Physical Institute in Moscow, where he is a chief researcher. He has worked for over 40 years in the human rights movements in the USSR and in Russia, 20 of them in close cooperation and friendship with Sakharov. Dr. Altshuler won the APS Sakharov Prize in 2014. The floor is yours, Boris. Unmute yourself, please.
Микрофон включите, пожалуйста, Борис. Микрофон.
Thank you so much. I greet everybody. Today I spoke 40 minutes in Lebedev Institute before Valerie Rubakov, who also spoke today. And now I'll speak 3 or 4 minutes. Thank you. I repeat, I greet everybody. And surely Sakharov died more than 30 years ago. And now the question is, why Sakharov? Why is he important at all? More that new generations came into life and they asked the same question. I must tell the heritage of Sakharov in human rights movement, public and politics, and also in science, in moral issues and in science. And I must tell something which is new now, because I prepared this book, which was published a few days ago here, Sakharov and Political Power, on the other side of the window. And I studied many declassified documents of KGB, of Politburo, and it happened that Sakharov proved to be very important for all the Soviet tops, beginning from Beria to Gorbachev, for all of them. They studied, he was really most important expert in strategic armaments, first 20 years of his work, and then in strategic disarmament after that, and saving mankind from the suicide in the thermonuclear war. What really, now I heard Sakharov said in his short interview, which was showed now, about his reflections of 1968. But what documents say? That these reflections were attentively studied by leader of the USA, Leonid Brezhnev, and he ordered to study another gods of Soviet Union, and also they were implemented. Here is Soviet United States agreement on moratorium on development of missile protection systems. Sakharov opposed it and he proposed it, and it was heard. All the politics of detente, because Sakharov said everyone who is on the brink of the abyss must make a step from it. And for the mankind to make a step from brink of abyss of thermonuclear war is to overcome this confrontation of capitalist socialist system. And detente began, and then Helsinki 1975 Act with its human rights basket. It was Leonid Brezhnev initiative. So everything would be, we can see visibly everything is okay. Sakharov is hurt. But now we come to the rather sad wisdom. Once it was 1973, I asked Sakharov why Brezhnev will not do something evident. And Sakharov answered me in the purely physical words, saying, he said, the higher the position, the less the number of degrees of freedom. Brezhnev can do very little. The same is true about Sakharov really was protected by very tops. And now from documents we can see that it was not only Brezhnev, but also chief of the KGB and Yuri Andropov. But there were other people under the carpet in Kremlin who hated him. And this protection was felt any moment because he was not punished for incredible things. But this protection by some tops was also limited. Brezhnev can do very little. And it was absolutely fantastic and paradoxical things. And I felt it even myself, how important it was the support of Western colleagues, physicists, and etc. I take a chance to take my special gratitude to John Archibald Wheeler, Joel Leibovitz, Bruno Koppe, many others who really made, it was difficult to understand, but something happened when there was the wave of this support of letters came, and we saw that all these so-called devils could not approach. You feel that you is protected, and we don't understand why. But it was really truth. When it became such a wave, and Sakharov was also protected. And so my gratitude. And I would like about Sakharov's as top expert for Soviet leaders. He said it to my father. They were good friends, worked together in nuclear installation. And my father is also the American Physical Society awardee of 1991. And my father said to him after Sakharov returned from exile, they met, and so they spoke about Gorbachev, Sakharov. And my father said rather standard phrase, Andrei Dmitryevich, you are on the top floor of political power. Sakharov immediately reacted. He said, I'm not on the top floor. I'm near the top floor, on the other side of the window. That I used in this my book. Hopefully it will be published also in English. I prepare now the mirror. Also, we prepared in Lebedev Institute this book. It was presented also today, re-edition of scientific collection of Sakharov scientific works. And I want to tell my gratitude to Stephen Coley from Princeton on fusion, to Bruno Koppe. And I would like very shortly in the end to comment on fusion topic now, because I spoke today, it's here. There is some similarity of ITER, giant ITER project, and gravitational instability. Gravitational instability, when there is big mass, it attracts another mass, it becomes more massive, it attracts even more, and it's avalanche is instability. The same about enormous financial programs like ITER. They are financially heavy and they attract more and more money. And this process already doesn't depend on the expected success of the project. It's pure bureaucratic attraction, instability of financial attraction. And the sad thing is that it really, because of it, many other parallel and not so expensive projects of research of hot plasma are really closed. And there are special reports of National Academy of Science of the United States. It's a report of 1919, and of American Physical Society of 2020, that, of course, we cannot close ITER. ITER must be supported by other directions of its research of hot plasma must be developed. So thank you. I think that Sakharov is with us.
Thank you very much, Dr. Altshuler, for your greetings and for your reminiscences. I see other people waving at you, who you have worked with in the past. Now we will hear from Marina Sakharov-Lieberman and Tatiana Yankelevich-Bonner in a recording made a couple of weeks ago because they could not be here in person today. So it's 39 minutes long, very interesting. So please play the video, Ebony. Good afternoon and welcome to the fourth session of our Sakharov-100 celebration, during which we will be reflecting on Sakharov's world with the help of two relatives who knew him well. I am Cheryl Spencer of the Forum on Physics and Society, and I am delighted to be here speaking with Marina Sakharov-Lieberman and Tatiana Yankelevich-Bonner. And we are recording our conversation early in May because they plan to be in Europe on the 21st of May, taking part in other celebrations of Andrei Sakharov's 100th birthday. I will introduce both Marina and Tatiana, and then they will spend about 10 minutes each to tell us about their current projects concerning Sakharov's legacy. That should leave us about 15 minutes to talk about their lives with Sakharov. Marina Sakharov-Lieberman is Andrei Sakharov's granddaughter. She is the daughter of Sakharov's eldest daughter, Tatiana Sakharov. Marina is a graduate of the physics department of Moscow University and a graduate of Stanford University. Currently, she is a business consultant. She is a board member of the Andrei Sakharov Foundation and a board of trustees member of the Andrei Sakharov Science Endowment, which was started through her initiative. She will tell us more about the programs of the Sakharov Endowment and some centenary projects she's involved in. Tatiana Yankelevich is the daughter of Elena Bonner, who was Sakharov's second wife. Ms. Yankelevich is a retired educator of Soviet history and the Soviet human rights movement. In the 1980s, Ms. Yankelevich campaigned extensively on behalf of Andrei Sakharov. From 2004 to 2009, she headed the Sakharov Program on Human Rights at the Davis Center for Russian and Eurasian Studies at Harvard University, which is now the home of the Andrei Sakharov archives. She is now an independent researcher affiliated with the Davis Center. She will tell us more about these programs after Marina has spoken. So please go ahead, Marina, and share your screen and give us your talk.
Thank you very much, Cheryl. It's great to be here today, if remotely. I'll try to start sharing. And do you see the full screen? Is that all right?
Yes.
I'm gonna talk about, both Tatiana and I work together on a lot of projects, and we both joined the organizing committee in Russia dedicated to celebrating Sakharov's 100th birthday in Russia. The first initiative that is mentioned here, in no particular order, is just the one that I have initiated, and that was starting Andrei Sakharov Science Endowment Fund to award scholarships to gifted students in physics. Lebedev Physics Institute, also known as FIAN, will hold a physics conference in May 2022, delayed by a year due to pandemic. In Nizhny Novgorod, there will be a music festival that will start on May 21st, celebrating Sakharov's 100th birthday again. There are lots of other initiatives of the organizing committee, but I should mention that the Russian Academy of Science is behind a lot of initiatives, and they're all listed on their website, Sakharov100.ru. There are also new coin minted by the Russian Central Bank and postal stamps and envelopes. Sakharov Center in Moscow will hold an international conference, Alarm and Hope, in May of this year. Several other conferences have already taken place, and they were also dedicated to Sakharov's 100th birthday. There will be a new monument unveiled to Sakharov in Sarov, the secret town where Sakharov worked for 20 years on the thermonuclear program. We were hoping there will be a monument in Moscow, but those plans have not yet come to fruition. And lastly, the grand event of the celebrations in Russia will be the concert at the International House of Music in Moscow. I wanted to talk a little bit about the initiative into which I put personally a huge amount of energy and effort in over the past few months. I really wanted to have Sakharov's name known in the scientific community among the younger generation of physicists. So to that end, we registered an endowment fund in Moscow, and leading physicists, including 2 Nobel laureates in physics and the president of the Russian Academy of Science, joined the board of trustees. The aim of the endowment is to help talented physics students professionally and financially. And this year, the fund is in position to award at least 15 annual scholarships to the students at Moscow Institute of Physics and Technology and the Physics Department of Moscow University. In addition to that, we will have 3 PhD students who will go through the full course of their studies at the leading universities in England, Switzerland, and Singapore. And we have further plans, and we hope that we will be able to work on more scientific exchange and with the students that will be selected this way. This is just a screenshot of the website of the Andrei Sakharov Science Endowment Fund. The pictures you see is Moscow University, Moscow Institute of Physics and Technology, and the building of in the middle, it's Lebedev Institute, because we hope that some of the Sakharov scholars will be doing their will be studying for their graduate degree on working at this institute where Sakharov worked himself. I don't know if you see the bottom of the screen, but we wanted to make available the scientific publications of Andrei Sakharov. So they will be available through the website of our endowment, but we are also putting them in other websites. Talking about scientific legacy of Sakharov, I mentioned already this international physics conference that the Lebedev Institute is organizing at the end of the centennial year, as we now call it, in May 2022. I will come back to this slide perhaps a little bit later, and probably since it's the last session, people have talked a lot about the meaning of Sakharov's scientific work today. But I wanted to mention the new publications we've been working for the centennial. On the left, you will see the cover of A4+ format album that the Lebedev Institute put together. I will share a few pages just to give you a flavor, because it's a unique publication with hundreds or scores of photographs that have not been previously seen, as well as regional documents. And on the right, you see a very cheerful new cover with the Centennial logo in the middle. And that's the full volume of scientific works of Andrei Sakharov, with the modern comments by the leading scientists, some of whom are present here at this APS meeting. In addition to that, we put together a volume of memoirs about Sakharov by his friends and colleagues and physicists and politicians. There are, I think, 10 Nobel laureates who wrote about Sakharov for this volume, and 2 former heads of state. So that's a pretty interesting book. And the one listed last is by Boris Altshuler, who is also the laureate of Andrei Sakharov Prize awarded by APS. and he wrote a very interesting volume called Sakharov and Power. These are just a few pages from the album Sakharov biography in photographs that I mentioned. And this page shows some of his colleagues who are also very well known. Yakov Zeldovich, another Nobel laureate in physics, Vitaly Ginzburg, and Sakharov's favorite teacher and PhD advisor, Igor Tam, who was also Nobel laureate in physics. These are a few more pages. This is the original handwriting of Andrei Sakharov describing his ideas on building thermonuclear weapons. This is Vitaly Ginzburg, who headed in later years the theoretical department of Lebedev Institute in Moscow. This page is called 7 Years in Exile, and on this page you can see my grandfather and my mother in Gorky, and on the top corner is myself. This is my grandfather and my step-grandmother in Gorky, and his scientific work that he carried on during his exile with a dedication to my step-grandmother. It says, dedicated to Lucy, her nickname. And this few photographs after the exile, Sakharov and Zeldovich at some conference, and Sakharov visiting Stephen Hawkins at Cambridge in England. Lastly, the album has 260 pages, so literally it's just a very small flavor that I'm presenting here. But this is in memory, and here on you can see the newly minted coin in silver that is that just came out in Russia, and envelopes and monuments in different places. And the golden medal is by the Russian Academy of Science, that is awarded every few years to leading physicists. So this is just some flavor that I wanted to give you of what's going on in Russia. There are also lots of events in different cities that perhaps Tatiana would like to mention, or we can discuss later on. But basically, thank you. That's it.
Right. Well, thank you very much, Marina. That is an amazing amount of activity and honorific things that are going on. To have a coin minted in one's honor, that is amazing. Is it going to be just a coin for putting on your mantelpiece, or will it actually be in circulation? Do you know?
The value of the coin in circulation, the official value is very small. The purchase price is much higher, about $40, because it's 15.5 grams of silver. So it's more of a collector's item than a circulation coin, and there are 5,000 coins minted presently.
Okay, so maybe we'll find out how, if we're allowed to buy them from the US.
I think that's a possibility. We plan to import some to the US.
Okay, that's good. I was looking at your pages from the book. It appears to be in Russian. Am I correct?
That's right, but the plan is to publish the English version for May 2022 physics conference at the Lebedev Institute. So we will have the English version as well.
Okay, that's great. Okay, I'm going to ask Tatiana to speak now about her activities. Thank you, Tatiana. Unmute yourself.
Cheryl, thank you very much for your kind introduction earlier. And thank you, Marina, for your incredibly impressive list of achievements that I know took a lot of energy and dedication and intelligence and shrewdness, I should say, on your part. And you are truly a Sakharov, a granddaughter, as I used to say. I want to apologize to everyone that I will disappoint somewhat. First of all, probably disappoint Cheryl, because I will not be sharing some of my my projects or my reminiscences about my stepfather. I would rather dedicate the time I'm given to use this opportunity to appeal to the community of physicists, of colleagues, whom Sakharov believed to be his natural habitat throughout his life. And I want to follow in his footsteps, to appeal to this community and to gather forces to do what he has called upon his colleagues back in 1981. And I will speak about his concept of responsibility of scientists. Let me start by reminding you that back in 1981, Sakharov, while in bitter Gorky exile, he was working on an essay that he called The Responsibility of Scientists, exactly that. It was an essay, or rather an appeal, that was addressed to the gathering in his honor, on his in the honor of his 60th birthday. The international conference in honor of Andrei Sakharov was sponsored by the New York Academy of Sciences, the American Institute of Physics, and the American Physical Society at Rockefeller University in New York on May 1st, 1981. That was the year when Sakharov turned 60. He finished writing his appeal, his greetings on my birthday, which I was really deeply moved to find the date under these greetings. At that meeting at Rockefeller University, which I remember very vividly, many of your colleagues and many of my friends took part. Among them were the late Sid Drell and Vicky Weisskopf, whom I remember dearly, and who, especially Sid Drell, became very close friends of my family. And the Chudnovsky brothers, no relation to Evgeny Chudnovsky, who I hope is here today. The Chudnovsky brothers took part in that conference, who were also dear and still are dear friends of our entire family, and who were the editors of the first collection of Sakharov's scientific work, published in the 1980s. In his appeal, Sakharov called upon the international scientific community not to remain indifferent to the fate of their colleagues in the Soviet Union and in other countries where free exchange of ideas is fraught with persecution. In his essay, he named 55 prisoners of conscience in his own country, the USSR. One of them was biologist Sergei Kovalyov, whose trial in 1975 took place on the same days the Nobel Peace Prize ceremony for Sakharov in Oslo, and whose trial Sakharov was prevented from attending by the KGB, same as he was prevented from attending the Nobel Peace Prize ceremony in Oslo. Years later, Kovalyov, now a free man and not a political prisoner anymore, summarized Sakharov's moral makeup, and I quote, "He was the bearer of thinking based on reason. His intellectual work, whether it concerned science, politics, or the struggle for human rights, was fully in line with the qualities that define a true scientist. These qualities can be reduced to 3 freedoms. He was free of fear, of selfishness, and free of prejudice. Is it new morality? No, it is the most ordinary human morality, only very consistent. The ancient legends of mankind tell us that the fruits of distinction of good from evil grow on the tree of knowledge. Ordinary human morality, unlike that of the saints and the prophets, is based on reason and on nothing else. And Sakharov's consistency in the implementation of moral principles is simply another name for intellectual responsibility, the responsibility of the science. End of quote.
I didn't say it again. I didn't.
I'll read remotely. On the day that marks Sakharov's
okay.
Concept of moral intellectual responsibility. Those of you familiar with that appeal, that essay called The Responsibility of the Scientist, would have noticed the special place Sakharov assigns courage, integrity, and honesty as essential to the fulfillment of one's responsibility, because they make it possible to resist the temptations and habits of conformity. I find it bitterly sad and grotesque that most of which Sakharov wrote in his address back in 1981 is present in today's Russia. It is, to me, inconceivable that many representatives of Russian cultural and scientific elite, the so-called and admired intelligentsia, that these people support, advocate, or even put forth ideas that go against everything Sakharov believed in. I am referring, you will guess, to the amendments to Russia's constitutions. These amendments allow the president to remain in power almost indefinitely. They effectively end the separation of state and church. They discriminate against Russian citizens of non-Russian ethnicity. And these amendments make any criticism of the powers that be a criminal offense. I find it morally deplorable and macabre that today, as Russian power structures are hard at work to turn the country back again, there is a clear trend to immortalize and perpetuate the memory of henchmen like Dzerzhinsky, Beria, or Stalin, responsible for crimes against humanity and mass murder of tens of millions of the innocents. The committee that was created by the order of President of Russia to mark the 100th anniversary of Sakharov's birth included in this committee included in its plans for Sakharov's centennial erection of a monument to Sakharov in Moscow, the city of his birth. I find it Kafkaesque and Orwellian that Sakharov has to compete with ghosts of totalitarian past, whose main merit was the suppression of human rights and freedoms and the construction of a so-called strong state at any cost. Today, the Federal Security Bureau, the FSB, proudly declares itself a direct heir to the KGB, and it practices the extrajudicial murders of Kremlin opponents with internationally prohibited chemical weapons. It's worth, I think, pausing for a moment to think just how extraordinary that is. A European government in the 21st century is operating a professional squad of assassins tasked with killing its opponent. Let me remind you that back in the 1930s, in the midst of great terror, Vladimir Vernadsky contemplated the place of free thought and moral responsibility of a scientist as a free individual in civic sphere. He considered it essential speaking the truth with no concessions. This was particularly difficult under the Soviet regime, with its total ideologization of science and destruction of scientists' independence. The Soviet scientific community could hardly aspire to Vernadsky criterion of a scientist's moral responsibility, even when the total control was eased up after Stalin's death. The fear remained for one's safety. And even when that fear diminished, the desire persisted to preserve comforts of the privileged class. Sakharov was one of the very few to have the intellectual courage and idealism to speak his mind. Many conformists and opportunists saw him as God's fool. Some, including the predecessors of today's cultural and scientific elite, and even the then president of the Academy of Sciences of the Soviet Union, proclaimed him insane. And as it turns out, he saw farther than most of them. Today, the international scientific community faces new challenges. Ethical issues continue to be no less acute than in Sakharov's time. Scientific and technological advances continue not only to benefit humanity, but also to strengthen authoritarian regimes, fuel the arms race, or be used for irresponsible enrichment. A new challenge is presented by the need for effective coronavirus cure. Another responsibility is to continue preventing our planet's self-annihilation in a nuclear confrontation. And much like in the times of Sakharov, there still remains a duty to defend colleagues and other unjustly persecuted, wherever these injustices may be taking place. Today, this duty is particularly poignant and urgent. And in closing, I want to call upon all of you to follow the path taken by Sakharov, Kovalyov, and others to defend those persecuted today. As Sakharov put it, and I quote, "Concerted actions in defense of the repressed will help ease their fate and strengthen the international scientific community, its authority and effectiveness," end of quote. Please remember that he believed that taking the path of active and selfless struggle for human rights would change something for the better in the moral image of our world. On a less romantic note, Sakharov believed that a moral choice always proves to be a pragmatic one in the long run. And I want to put my trust in your pragmatism. Thank you very much.
Thank you very much, Tatiana, for a very strong statement there, a reminder of what has happened in the past and the unfortunate fact that we don't seem to have progressed very much from when Andrei was persecuted and sent to exile and mistreated. So I am happy to say that after this session, the second half of this fourth session, we'll have the current chair of the Committee on the International Freedom of Scientists of the American Physical Society. And he will be telling us more about what that committee does. It does try to help. Unfortunately, we have scientists here in the US who are being persecuted unfairly for what should have been a minor academic failure, just a small thing, and yet they have been arrested by our Justice Department. So thank you for your call to action, and we hope that the people watching this webinar will take up some of your suggestions and improve the situation, in fact, just for society, not just for scientists. So thank you very much. So we have now, I reckon, about 8 minutes left to continue our conversation. speaking of the mistreatment of Sakharov and Bonner. So Marina, would you like to tell us, I believe you visited them in Gorky, and can you tell us how he actually managed to keep going his scientific work in those years, 1980 to 1986, when he was in Gorky?
Yes, so Andrei Sakharov and Elena Bonner were almost in complete isolation. And from the moment that Elena Bonner was also exiled to Gorky in 1984, their situation grew much worse. Only children of Andrei Sakharov and myself as a granddaughter and scientists were allowed to travel. And scientists, that was an interesting story because they, the physicists at the Lebedev Institute used a very clever way to kind of game the system. They said Sakharov is not sacked from the institute, right? So he has to continue his scientific work. And if he is to continue his scientific work, he must attend the seminars at the institute. But if he cannot attend the seminars in person, then we have to bring them over to him in Gorky. And this way they were able to secure permission to travel to Gorky. And usually, I think they went in pairs. Vitaly Ginzburg personally made a number of trips. Some of the people here have been to Gorky as well. When Andrei Sakharov returned to Moscow after 7 years of exile, Ginzburg made quite a famous statement, because not only scientists carried the physics papers and discussed physics, but sometimes they carried back letters that Sakharov wanted to send over to the open world and to the United States. And Ginzburg mentioned 7 years, so many trips, not a single scoundrel among us. Nobody reported to the KGB what they were up to. And I have to say that on a personal level, both Ginzburg and Zildovich made a point of taking care of me in my grandfather's absence. They were saying they had a duty to help me with my physics studies, which was kind of nice.
Okay, thank you. So, so I'm assuming that the speech that Tatiana mentioned about the responsibility of scientists, he wrote while he was in Gorky.
Yes, it is.
And that was distributed by this method that Marina has told us about, that other scientists visited him and then they would have taken the speech and got it distributed. So the conference at the Rockefeller University, I'm a little confused. That was when?
It took place on May 1st and May 2nd of 1981. And as a matter of fact, I have, to my surprise and delight, I found that Sakharov's greetings, Sakharov's appeal, is published by the New York Review of Books in their May issue. And it can be seen by anyone free of charge, as long as they register for that particular article, and can be copied and saved for the whatever archives people wish to keep, including American Physical Society would be able to have that in their archives. And a little detail, maybe clarification of what you said. In 1981, the colleagues, physicists from Physics Institute of Academy of Sciences were not yet traveling to Gorky, at least not in the beginning of 1981. It began a little bit later, and my mother was still free to travel between Gorky and Moscow, and she was the conduit. She was the courier, often at great risk to her safety. she would be the link of Sakharov with the outside world, and practically everything that was published in the West until 1985, when she was arrested in Gorky, came to Moscow with her. And we have received it here in the United States. It was translated into English and turned over to New York Review of Books and published in time for that conference.
Okay, so you are in fact associated with some archives at Harvard University of Sakharov. So how extensive are those, and are people allowed to visit them if they're doing research on Sakharov?
Oh, absolutely. One exclusion from the Harvard rule, Harvard, which is extremely stingy about anything it owns, is quite generous with the archives, and anyone who comes to Harvard is able to request to see the holdings of the Sakharov archive. Some of them are still restricted for publication, but most of them, and definitely scientific works, are possible to quote from and to work with for any researcher, of be it a physicist or a historian of science or any other historian. And I want to mention that we have his earliest scientific paper, which is the, I think it deals, Marina, correct me, it has to do with the multi-leaf model of the universe, with the turn of the arrow of time arrow. And I think that was his PhD, or as we say in Russian, kandidatska dissertation. So this was became his interest, his professional scientific interest early on, what you have mentioned as astrophysics, which more than that. It's actually the universe development and the Baryon asymmetry of the universe, which is now one of the major directions in scientific research.
Okay, so unfortunately, I see us approaching the end of our time allotment here for this session. And you have mentioned several things.
Am I interrupting? I just wanted to add a couple words, because in this session, I guess we are together with two more people, and I looked up Zafra Lerman, who is recipient of Andrei Sakharov Prize this year. I wish we could have a live dialogue, because I think we share the same beliefs that scientific exchange and seeing face-to-face is extremely important. And I hope that now the political dialogue has turned a bit frosty, and the tourist exchange is perhaps also not thriving, but it's even more important to keep the scientific exchange going. I hope that our Andrei Sakharov Science Endowment will be one of the conduits of this scientific exchange. But in general, I think it's really critically important for scientists all over the world to be in this dialogue and to influence their governments about shared ethical values as well as scientific endeavors.
Thank you. Yes, indeed. Science diplomacy is what we call it, and it actually continued all through the Cold War, and we are trying to continue it even today, but especially between the US and Russia and China. So thank you very much, Tatiana and Marina, for these very interesting talks, and for Tatiana's reminder about the responsibilities of scientists, which we will strive to follow. And I'm going to close this session now. Thank you very much. Bye-bye.
Thank you, Cheryl.
Thank you.
Okay, here I am back again. I'm live now. I hope you enjoyed that recorded conversation with Marina and Tatiana. And Tatiana made a very strong statement about the responsibilities of scientists. We are responsible to speak out about the suppression of academic freedom. And that topic is what our next three speakers will cover. First will be Zafra Lerman, who I will introduce now and ask her to turn on her video camera and unmute herself while I give her introduction. Zafra Lerman is the president of the Malta Conferences Foundation, which uses science diplomacy as a bridge to peace in the Middle East. For more than 25 years, she chaired the American Chemical Society's Committee on Scientific Freedom and Human Rights. She worked on human rights cases in the former Soviet Union, Russia, China, Guatemala, Cuba, Peru, and South Africa. She has received many awards, including the AAAS Award for Science Diplomacy in 2015, the APS Andrei Sakharov Prize in 2016. She has been nominated for the Nobel Peace Prize by a member of the US Congress and a member of the French Parliament. Please go ahead, Dr. Lerman, with your remarks.
Thank you very much. I want to thank the APS for inviting me to participate in this symposium. I want to thank to all the people that are still with us, because I checked the number and I see how they are falling down. So thank you for still being with us. I want to thank Marina for mentioning me in her video. It was an honor and a surprise to hear it. I will share my screen with you and will show you several slides. Let's go to full. Am I doing full? Let's look here. I see myself and other people on half of my slides, so let me see if I can delete and have a full screen. Usually let me do it, but this time...
No, it is looking okay on my screen.
Oh, now it's okay on my screen. I want to concentrate on from fighting for human rights to use science collaboration as a bridge to peace. And the pictures you see here are the places that I work mainly on human rights and science diplomacy and collaboration. I had the privilege to meet with Andrei Sakharov in 1988. The occasion was when I served on the executive committee of the Albert Einstein Peace Prize Foundation. In 1988, we awarded Andrei Sakharov in Washington with the Albert Einstein Peace Prize. I had the privilege to meet with him and talk to him and explain to him my activities in the Soviet Union. And based on his advice, I took a crash course in Russian before I returned back to the former Soviet Union in order to be able to do my activities without needing a translator. His advice to me was never let up on pressure one applies on governments or organizations that abuse human rights. And I led my life by his credo. I have to mention, when we talk on human rights in the Soviet Union, I have to mention the Committee of Concerned Scientists that was extremely involved with the Soviet Union and with the refuseniks very early. I serve as the vice chair of the board for chemistry on the Committee of Concerned Scientists. And in 1978, the Committee of Concerned Scientists joined other American scientists to create the international movement that was called SOS, Scientists for Sakharov, Orlov, and Sharansky. I had the privilege to meet personally with Sakharov and to meet with Yuri Orlov too. When I went to the Soviet Union, I always went with a group of chemists, and they were my cover-up of what I really wanted to do. So with a group of chemists, we did science diplomacy. We met we were guests of the Mendeleev University in Russia and the St. Petersburg State Polytechnical University. By that stage, it was Leningrad. We gave lectures, we held lectures, and we tried to form collaborations with our colleagues in the Soviet Union. This was the science diplomacy by day. But then at night, I moved to human rights. We arranged it before I arrived that there will be a refusenik waiting for me after midnight in a dark alley. And before I left, I looked for a brave person in my group of chemists. Usually it was a woman. And I said to her before I left, I said, don't ask me questions, but if I'm not here for breakfast, please call the American Embassy. And then I went and met with one refusenik that we continued and met few more. And then we went to an apartment house. It was already close to 2 o'clock in the morning, where they were like 50 dissidents, mainly refuseniks. I brought with me a lot of scientific material to share with them. And I gave a seminar. The Committee of Concerned Scientists was very, very involved in delivering seminars to the refuseniks in the Soviet Union. The most important thing is that I took all the CV back from them, and in the purpose of bringing it to the US so we could work on their behalf and help them leave the Soviet Union. Few wanted to live for Israel and few wanted to live for United States. For sure, all these activities were illegal, and I was very happy that nobody had to call at breakfast the American Embassy, and I did it every night, both in Moscow and Leningrad by them. I wanted to read to you a letter I received for one of these refuseniks that was sent in 1984 for labor camp in Siberia. And he was released with all our efforts in 1987 and came to the US. I met him in Chicago. And since then, we developed a great friendship. His name was Yuri Tarnopolsky, and he wrote, I often wonder what could make a person living in freedom, safety, and comfort to fight for somebody deprived all that and languishing somewhere on the other side of the globe. I realized that both the faraway victim and his American guardian angel had something in common. They had the same ability to go against the tide, and they did for science something which could hardly be rationalized, an exhausting, messy job of fixing its very foundation, invisible on the pages of professional journals that kept science both human and humane. I always like this statement from Yuri Tarnopolsky. The work had continued in Russia, and instead of having to deal with the KGB, we had to deal with the FSB. You can see that the C-SPAN recorded this talk that this is Alexander Nikitin, that was a nuclear engineer and worked with submarine, but he worked with the Bologna Environmental Foundation in no way an equal attention for the nuclear material that was poured in the North Sea, and he was arrested. And I managed to go several times, meet him when he was released to house arrest, meeting him in a basement, and by the year 2000, before the charges were dropped against him, we managed to bring him to Washington to an American Chemical Society meeting where he addressed more than 1,000 ACS members, and all the media, both in the US and Canada, covered this talk because this was the same time that the Russian submarine went down and they could not save the people, like 50 people died in that, and this was the high interest to talk to Nikitin. In 2001, after September 11, I suggested to our ACS Committee on Scientific Freedom and Human Rights, which I chaired from 1986, from its inception till its death in 2010, that after September 11, we have the responsibility as scientists to use our science for achieving peace in the world. And sadly today, the situation in the Middle East is as hectic as it was then. Today there is a ceasefire between Israel and Gaza, but we started working in 2001. You can see all the countries that participated, and the idea was to bring
Dr. Lerman, you have 2 minutes.
Okay, to bring scientists from all these countries to work together and develop collaboration that can lead to peace. And this was the science diplomacy. We are now, this year, we'll have the 10th conference, and a lot of collaboration was formed. These people had influence on their governments, and the effort of these Malta conferences still exists. In every conference, we have several Nobel laureates. They have a lot of purposes, because the scientists always can say that they are going to interact for 5 days with Nobel laureates, where they will never have this opportunity. And thank you very much, and you can follow us in this website. Thank you.
Thank you very much, Dr. Lerman. And we will be taking questions in the Q&A box. You can type them in anytime, but we won't actually be answering them until after the next 2 speakers. And that will depend on how much time we have left. So I'm going to introduce our last 2 speakers. And if Dr. Lerman could stop her video and we could bring up Dr. Kabanov now. Alexander Kabanov is a distinguished professor and director of the Center for Nanotechnology in Drug Delivery at the University of North Carolina in Chapel Hill. He's also a professor of chemistry at the Moscow State University, where he got his formal education and degrees in the 1980s. His honors include the Lenin Komsomol Prize, an NSF Career Award, and the George Gamow Award. He was elected to Academia Europaea and the US National Academy of Inventors. Professor Kabanov is a corresponding member of the Russian Academy of Sciences, and he is the immediate past president of the Russian American Science Association. I will also tell you the second speaker will be Peter Vorobiev. He is Halliburton Professor and Associate Chair of Mechanical Engineering at the University of New Mexico. He received his MS degree in Applied Mathematics from the Moscow State University, and his doctorate is in Mechanical Engineering and Applied Mathematics, which he got from Lehigh University in Pennsylvania. Peter serves as the chair of the American Physical Society's Committee on International Freedom of Scientists. So Alexander, would you please go first with your slideshow as fast as you can, please?
I'll try to do that. Can you hear me well?
Yes, I can. Yes, you're fine, and we can see your slides. Thank you.
Excellent. Well, first of all, it's my great honor and pleasure to speak today and to share perhaps some thoughts based on my over quarter of century experience of working in the United States and keeping very strong connections with Russian science in the last 10 years, in addition to my main appointment at UNC Chapel Hill, being a secondary appointment at Moscow State University. So I guess I want to give my the way how my view from both sides of the mirror of the Sakharov's world, and that's how I called my presentation: Stand United to Combat Global Assault on Truth, Peace, and Human Rights. As already was mentioned, today, US scientists currently are being prosecuted, charged, and arrested in the name of combating economic espionage by Department of Justice and US government as a whole. And there are numerous cases. Dozens and hundreds of scientists are under suspicion. It's mainly targeting collaborations with China. Most recently, there was a letter which I recommend everyone to read. This is a letter, a call to save Professor Charles Lieber, one of the most notable cases. I don't want to go into details. Generally, I can tell you that accusations against Professor Lieber include or are based on incorrect filling of some quite ambiguous forms and reportings, and they are of great concern, as well as accusations against Professor Chen. More recently, we became aware that Congress may impose funding ban on US researchers in so-called talents programs in China, Russia, Iran, and North Korea. This is about very important, in my view, to United States Endless Frontier Act to dramatically increase funding of science, which is, of course, in United States, which is, of course, overdue. And we, of course, understand the need for protecting intellectual property and essentially making sure that the funds directed to research in the United States help United States as well as the entire world. But the language which is currently included in this bill, project of a bill, is a concern. If it is approved as is, it would lead to very significant and damaging consequences. It has, in particular, super broad definition of talents programs, which is defined by the presidential memorandum on January 14, 2020. And it's so broad that it would ban normal academic activity, including teaching, education, participation in academic advisory boards, academic societies, reading charging documents against Professor Lieber, whom I mentioned before. One of his transgressions was that he was elected to the Chinese Academy of Science. This bill in the United States could put in jeopardy Americans and citizens of other countries. For example, those who might have legal obligations under some contracts which were perfectly fine before this bill, but then could become prohibited or banned in the United States, and it is counterproductive to the United States. It could deter positive collaborations, result in exodus of scientists abroad, and so on and so forth. Now, let me switch to Russia. One thing I want to mention is that nearly 1,000 Russian-speaking scientists recently, in February, wrote a letter which is focusing on stop growing confrontation and turn to cooperation and dialogue. This letter has been signed originally by over 100 scientists, including 2 living Nobel laureates of Russian origin, many members of various academies, including Russian Academy, and was joined by nearly 900 scientists after it was published. So it's almost 1,000 people letter. And I recommend everyone to read not just this letter report in Nature, but the original letter, which is available in English and in Russian. Essentially, this letter calls to opposing the chemical weapon. It calls to Russian authorities to respect citizens' right to protest peaceful and establish dialogue with society. And it calls to turn international cooperation to combat global threats. And this particular demand or call is not just addressed to Russians, it is addressed to American government as well, and generally to the entire world. Now, why this letter was written by Russian academics? I guess the short answer is because it was impossible not to write. And what is also very important, that this letter refers to peace, progress, and human rights. These 3 goals are insolubly linked. That's a phrase from Andrei Sakharov's Nobel lecture. Now, if we look at Russia, numerous scholars and increasing numbers are imprisoned, sentenced, and prosecuted for treason and other crimes. And often the prosecution goes in secrecy, so we even don't know what they are accused of. I know we don't have that much time, but I want to read each name. It's incomplete list, but I don't think these names were ever read in the forum of this international magnitude. So this is Viktor Kudryavtsev, physicist, Roman Kovalев, physicist, Anatoly Gubanov, physicist, Valery Mitko, Arctic explorer, Anton Kolomitsyn, historian, Alexei Vorobyov, space engineer, Alexander Fedutov from Belarus, political sciences, Yuri Dmitriev, historian, Andrei Zhukov, historian, Valery Golubkin, physicist, Azat Bevsakov, graduate student, Vladimir Lapygin, physicist, Natalia Sharina, librarian, and this list can be continued. And unfortunately, it is growing. Another important thing that is happening, it is a mass assault on popular science and education in Russia. So the amendment has been adopted by Russian lawmakers, which essentially bans any kind of educational activity other than those which are authorized by the state. So in order to give a lecture in Russia, you have to be, it has to be official. Even now, when we are asked to give talks, sometimes universities are requiring us that we sign a contract. And here comes the American ban on interactions with bad countries, which essentially puts the scientists in the block. They can be banned and prosecuted just for giving a scientific talk in Russia. It is opposed, this particular law, by scientists, including the Russian Academy of Science, educators, science journalists, and it has numerous number of negative comments, but it is happening right now. Now, I want to—
2 minutes.
Very good. I want to just reflect on what is in common between all these, I would say, conflicts that is happening? And my take on that, it is the conflict of populism versus professionalism. And it is also the conflict between grassroots and self-organization versus government regulation and control. And that happens across the globe. So this is a global conflict, and it's also is affected by international affairs and worsening the world. So our specialists in social sciences would advise us on the reason why it happens, but these are the main conflicts which we are facing. So what shall we do? First of all, I think we shall overcome, and we have to stand, and we have to stand united. We have to relate the suppression of academic freedom and collaboration by states to bigger issues which are discussed in different countries, such as peace, human rights, cooperation, and global security. We have to relate it to other ongoing conflicts in the states: equity, inclusion, Black Lives Matter in the United States, suppression of peaceful protesters and opposition in Russia, Belarus, and other countries, because they are all same in nature. We have to relate it to populism, anti-intellectualism, spread of untruths, and division, such as, for example, untruths about global warming. We have to unite in support of persecuted scientists today, oppose violation of human rights. I believe we should establish an international academic council on peace, human rights, and cooperation and global security to coordinate and improve understanding across groups of disciplines. And we have to be proactive, speak up, be heard, to address specific concerns, such as, for example, the concern on foreign collaboration ban. We have to talk about that. We have to try to change. Being silent is no option today. Thank you for your attention.
Thank you very much, Dr. Kabanov, for a very strong explanation of what's unfortunately still going on. You could stop sharing your screen, and I'm going to ask Professor Vorobiev now to talk about what the APS tries to do with regard to the international freedom of scientists. Thank you.
So,
go ahead.
I represent Committee for International Freedom of Scientists here, and the first thing, and probably the better known thing about what we do is we collect nominations and announce winners every 2 years for the Sakharov Prize. Let me share my screen and show you the only slide that I have. That is the description of the award. It recognizes outstanding leadership and achievements of scientists in upholding human rights. So essentially, the title of our today's meeting, Physics, Peace, Human Rights, the Legacy of Sakharov. Somebody who is true to it should be considered as a candidate for the prize. And I encourage everybody who is still with us to think about who could be nominated, because we are still collecting nominations. And the deadline for the nominations is June 1. So there is not that much time left. Now, on the bottom of this slide is the more detailed description of the award and instructions on how to nominate a candidate. And if you also type questions into the Q&A, I will be able to just copy paste the same link so that you can bookmark it. This, however, is just one thing that the Committee for International Freedom of Sciences does, scientists, my apologies. The other thing is less visible, but perhaps even more important. Although, of course, before I get on to the second thing, I would like to mention that the people that we recognize as winners of the Sakharov Prize, and I'm so happy that two of them are with us today in the same session. They are people very deserving of this recognition, and they are people who must be heard and appreciated. And sometimes actually who we select, we don't do it on purpose, but occasionally it sends a message. So for example, the most recent Sakharov Prize was split between Ayşe Erzan, who is a peace and democracy activist from Turkey, and who was actually imprisoned for a while after 2016 and that attempted coup and the purge. And the second person is Shaoxin Shi, who is an American researcher and also a defender of international freedom of scientific exchanges. So we didn't do it on purpose, but I think it sends a message. So moving on to the second task of the committee, we try to do our work mostly behind the scenes and actually help scientists all over the world who have been imprisoned, some of them for speaking out for human rights or for peace, some of them to scare others, some of them simply for being in the wrong time, in the wrong place. And we try to see what kind of advice we can dispense to the American Physical Society to support these scientists and get them to freedom. Because in most cases, well, not in most cases, but in many cases, there are criminal charges and there are arrests. And the last 4 months, the committee has been collecting information about 2 groups of scientists in 2 countries. And since these letters have not been officially sent out by the board of American Physical Society, I am not at liberty to tell you which countries are involved, but after having listened to Dr. Kabanov's presentation, you can make a very well-educated guess. So Sakharov's cause lives on. That's all I have to say.
Thank you very much. And now we have I know we've gone past 4 o'clock, but I think it's very important that we have brought all these topics up at the end of this very interesting webinar. And I am going to now bring the 3 speakers onto the screen, and hopefully I have got some of you, let's see, Zafra, here we are. You're all moving about. So Alan, you've been looking at the questions, and I'm hoping that you're going to pick out a few to address to our 3 speakers that are here. Could you help me with that? Could you speak some of them, please?
Yes, I can do that.
I'm still trying to bring up the view of the floor.
Well, shall I begin with at least one of the questions for Zafra?
Yes, please.
This comes from Emma Zaidella, who asks, I'm curious about your human rights activities in Cuba and China from the first slide. Could you tell us a little more about them?
I don't want to keep the people too long. You can talk about China and Cuba for a day, not for a lecture. Cuba was, both Cuba and China is similar to the Soviet Union. I always went with a group of people to do science diplomacy and forming exchanges and collaboration during the day, and then later I went to do human rights. In China, it was very tough because I met with dissidents in house arrest. Professor Xu was in house arrest. He was the second in command to Professor Fang Liji, who was called the father of the democracy. That, by the way, I hosted him as he came out from China, and he talked directly to China on Voice of America, directly from my office. When I was invited to give a plenary lecture, I explained that I'm in China very often and I see all the development, and they are because of the scientists that contributed so much that I invited to my talk, and sadly, they are still in prison. I called for their release and dedicated the lecture to them. The Chinese that do there did with the finger like that. The Americans that were in the room put their head down. Then they told me I could get all of them arrested. So, but China was harder because families did not collaborate like in the Soviet Union. Cuba was a completely different story. Even just to get to Cuba, we needed, as Americans, we did not have the scientific freedom to go to Cuba. We needed a license from the Treasury Department, and we interacted. As a matter of fact, I'm an honorary member of the Cuban Chemical Society. And then, as usual, in the evening, I tried to work on issues of human rights. So every country was different. China was very tough.
Very good.
Thank you. Another question, Alan?
Well, I do have one that combines Peter and Sasha. Sasha, you showed on your list of current jailed scientists someone named Vorobiev. Is there any connection between? Oh, no. Okay. On a little bit more serious note, this comes from the attendees. An excellent call, Dr. Kamenov, for scientists having to unite for the defense of human rights. Some medical doctors have been killed in Gaza. Many Palestinian scientists are in jail. Is there any activity yet organized around that situation?
Well, I think, can you hear me?
Yes.
Well, I'm calling right now for all of us to unite based on scientific and human rights principles and look at the global world and see the connections between different untruths and different problems. I do believe that there is a huge rise of populism, which is driving many and makes many conflicts worse. It's true for all nations, it's true for all countries, and international conflicts are just fueling this divide.
And at CIFS, we are actually following the cases of several Arab-Israeli scientists and, well, preparing some recommendations for the American Physical Society again on how we can help.
Right. So I would suggest that if you go to the APS's website, www.aps.org, and you drill down, you will find the Committee on the International Freedom of Scientists, and you will find Dr. Vorobiev's email address. And so maybe if you're interested in following Dr. Kamenov's suggestion of making a new group of people, that if you could channel your replies through the APS, we might be able to get something going. And Sasha, you are at the University of North Carolina in Chapel Hill. I'm sure you're on their website. People can find your address on that website. And so people can write to you also, right?
Yeah, yeah, absolutely. What I wanted to emphasize, which I probably should even make it stronger, it has to be cross-disciplinary. So we are dealing with kind of cross-disciplinary problem, and we have to give a cross-disciplinary answer. That's why we need to unite chemists. Here you have members of American Chemicals, 2 members in the screen of American Chemical Society, 2 physicists, but it involves medical doctors, as it was said. It involves everyone. It actually is a divide between intellectuals and professionalists. Professional scientists and others, and those who are populists. It's unity against divide.
Yes, indeed. So I see we are already 16 minutes past our official ending time. I see Vladimir getting all nervous over there. So I am going to unfortunately have to bring it's my task to bring the whole webinar to a close. It's been very interesting. We have been celebrating Andrei Sakharov's 100th birthday. I give thanks to all our esteemed speakers who have informed us about Sakharov's contributions to nuclear weapon design, to nuclear fusion, to fusion energy, to understanding the beginning of the universe, to nuclear arms control, and finally, his contributions to improving human rights. We have heard several calls to fight back against violations of human rights and the need to abolish nuclear weapons, which I hope you will all take to heart. You can rewatch the talks as they have all been recorded, and anybody who registered for this, and we had nearly 600 people register, but 220 were actually able to attend. You will all receive an email with a link to the recording, which I hope you will share with your friends and colleagues who were not able to join us today. It's been a very interesting 5 and a bit hours. When you have a recording, you'll be able to fast forward through the bits you are less interested in. But I think this last session on Sakharov and human rights and the current situation is very important. And Zafra's work on science diplomacy in the Middle East is even more important as we see what's going on there right now. So I thank you all, and I will ask our APS host, Ebony, to close this webinar. And I wish you all good health, a well-lit path, and goodbye. Thank you.
It's been an honor.